second round of final defense talks for the Young Scientist Award. Today's committee members, or that are at least here present in the room, are myself from the University of Twente, Martin Thuo from the North Carolina State University, Lan Fu, the Australian National University, Jure Gogocci from Drexel University, and Nicolas Pepas from the University of Texas. Well, I'm sure that most of you have seen us already before, so I will not go through lengthy introductions because I want to save all the time for the people it really matters is about, who it is really all around today, about today. And these are the following 9 finalists who will give a 50-minute talk followed by a 5-minute Q&A. So I would not like to steal any more time of the candidates and move forward to our first speaker, TANG Li from EPFL, who will be talking about multidimensional immunoengineering approaches to enhance cancer immunotherapy.
Okay, I'll start to share my slides.
Yes. Yeah, perfect.
Can you see my slides and hear me well?
Yes.
Okay.
The floor is all yours.
Okay, great. Thank you very much. First, I'd like to thank Alice, Christian, Nicholas, and all the committee members for this great opportunity to present my research in the iCANX talk. I'm Li Tang. I'm currently Associate Professor of Bioengineering at the EPFL, Switzerland. So today, I'm going to share with you a very brief overview of my research in multidimensional immunoengineering approach for enhanced cancer immunotherapy. As we all know that our immune system is an amazing system that involves many factors, right? Including primary, secondary, and tertiary immune tissues, such as spleen, lymph nodes, bone marrow, and also many of the immune cells, such as lymphocytes, T cells, B cells, and the numerous numbers of soluble factors, such as antibodies, cytokines, many of them. So they all working together seamlessly to protect us from numerous attacks of evading passengers and also disease cells in the body. So together, these are very important, delicate system that can protect from many of the diseases. So if anything goes wrong, either under protection or overreaction of our immune system can potentially leading to troubles such as diseases. So if we can control our immune response precisely, we can fight many diseases, right? Or prevent or treat these diseases. I want to share with you 2 recent phenomenal examples. So one, during this COVID pandemic, we all know that vaccine is very important. So as an emerging new type of vaccine, these days we can use engineered nanoparticles to very efficiently deliver this mRNA as antigen encoding components to elicit very strong immune response, particularly antibodies in our body, to protect us from these COVID infections, virus-based infection. So this already showing one power example that's how we can use engineering approach to enhance our protective immune response. In another phenomenal example is CAR T cell therapy, which is also an emerging therapy against cancer. So this CAR T cell therapy based on a very important immune cells called T cells in our body. You can collect these T cells from the blood of patients. But these general T cells, they do not necessarily recognize or kill cancer cells. So we have to genetically engineer these T cells to express a little structure called CAR receptor or chimeric antigen receptor on the surface of T cells. So once with this CAR receptor on the surface, these T cells are licensed to recognize and kill cancer cells. So next step is to expand these soldiers into a large army, and then you can infuse this army back to the patient to fight with cancer. Okay, this therapy has already achieved a dramatic high response rate in the clinic, treating liquid cancer such as leukemia. So if we want to really control the immune response well, we need to first understand how the immune system interacts with diseases. Here I'm showing you cancer as an example. So as we can imagine, these interactions, of course, is largely biological based, right? As you can understand that this involves numerous biological factors such as cells, receptor ligands, cytokines antibodies. Okay, these are very important biological interactions between our immune system and the disease. And targeting these biological interactions for sure can already control our immune response and already achieve great success. Here I'm showing you the example of a cancer immunotherapy. As we know that in the conventional therapy, such as chemo and radiotherapies, you rarely have a long-term durable response in the treated patient. Nowadays, with the emerging immunotherapies, we can achieve a very long-term durable response in a small portion of these patients. So taking immune checkpoint blockade antibodies, such as anti-PD-1, anti-PD-L1 as example, so you can block this suppressive biological interaction between the T cells and the cancer cells and reactivate these T cells to let them fight with cancer. And using this immune checkpoint blockade therapy, doctors can now already treat a very broad spectrum of different cancers. However, you can also appreciate one of the major limitations we still have today is the response rate still remain very low. So only 20-30% of patients, they can benefit from this new therapy. We are still very far away from an ideal immunotherapy that can potentially cure a large majority of the patients. So we can argue that something must be missing there to prevent us to have a very potent immunotherapy to benefit the patient broadly. So coming back to this interaction between our immunity and the disease. So besides these numerous biological interactions, I want to argue that don't forget about other dimensions, right? For example, the chemical interactions. Chemical factors such as the pH values, hypoxia, CO2 redox potential can also potentially impact our immune response. Third, in another dimension, physical dimensions, physical factors such as temperatures, stiffness, force, shear stress can also contribute to this interaction and control our immune response, but oftentimes underappreciated. So together, my lab want to have this idea that our immunity and disease interaction is a multidimensional, involving all these three different interactions, biological, chemical, and the physical. So in the past 6 years, leading an independent lab at EPFL Switzerland, my lab has trying to develop new approaches to engineer these multidimensional immunity disease interactions. And we have already developed research programs around target each of these different directions. So regarding the biological interactions, our focus has been understanding and manipulating the metabolism of our immune system, because this can help to reactivate some very tiring immune cells like T cells, or called exhausted T cells, and then make them to be able to going back to the battle to fight with cancer. Regarding the chemical interactions, my lab has developed several synthetic and material-based approach to modify the existing immunotherapies, making them specifically activated in the tumor tissues and reducing their systemic toxicities, and without causing damage to the healthy tissues. In the new dimensions, we are exploring a largely unexplored field, which is the mechanical interaction between, like, say, for example, T cells and the tumor cells, and understand how these mechanical factors can also impact the outcome of immunotherapy. So some of my research already made an impact in the clinic, and I have co-founded a startup, Lemon Biotech, and successfully raised the seed fund, and now we are going to launch a clinical trial very soon next year. So in the next of my talk, I'm going to give you a very brief example in each of these research directions. So first, in this mechanical immunoengineering direction. So here I'm showing you the famous cancer immunity cycle. You don't need to read every of these steps, but you can understand that there's many steps are involved to eventually have very strong anti-tumor immunity against cancer. However, cancer is such a sneaky disease. It develops all kinds of different suppressive mechanisms to block this immune response and eventually make your immunotherapy fail. However, the efforts so far in the field is almost exclusively focusing on understanding and control the biochemical immune suppressive mechanisms and develop new therapies to overcome this immune suppression. Over the past few years, many of the research have already shown that there's another important aspect of this cancer immunity cycle. Many of the mechanical factors, such as cancer cell stiffness, dendritic cell shape, lymph node stiffness, shear force in the circulation, T cell forces, all can contribute to this anti-tumor immune response. However, how these mechanical factors can potentially impact outcome of immunotherapy remains largely unknown. So in one of the recent research we reported last year, we are trying to understand how the T cells can exert mechanical forces between the interface between T cell and the cancer cells. We identify a new mechanical suppressive mechanism, which is the softness of the cancer cells. This is because of the cancer cells, as compared to normal cells at the single cell level, they are oftentimes softer, than their normal counterparts. This has been known. And we further identify that this softness actually serve as a mechanical immune checkpoint, can help the cancer cells to evade the T cell mediated killing. So this is because when the T cells encounter a soft cancer cells, so this softness will impair the T cell force exertion at interface between the T cell and the cancer cells, also called immune synapse. And the reduce of this force exertion will impair the T cell mediated killing and eventually help the cancer cells to evade the T cell mediated cytotoxicities. In other words, T cells fail to kill these soft cancer cells. And we further develop a stiffening intervention that we can stiffen the cancer cells, making them stiffer than normal. And now they can become more sensitive toward the T cell mediated killing and eventually enhance substantially the outcome of cancer immunotherapy. So we can combine this stiffened intervention with current immunotherapy such as CAR T cell therapy or checkpoint blockade therapies and enhance the response rate in cancer patients in the future. So in another efforts, I want to share with you the discovery of a new way to reinvigorate terminally exhausted CD8 T cells. As I mentioned to you that the T cells are soldiers. Once they get into the tumor, they keep fighting with cancer cells, but quickly they will get tired and they losing their capabilities to keep the fighting. So these T cells are called exhausted T cells. So there are two important subsets of exhausted T cells are important for the fight with cancer. One is so-called progenitor T cells, or simply call them progenitors. The other is terminal exhausted T cells. And these T cells actually are very important because they are killer cells. They secrete the most of granzyme B. But the problem is, as compared to the progenitors, these T cells are short-lived. They lose their capability to proliferate or self-renew. And most importantly, we found that all the current cancer immunotherapy, including checkpoint blockade, they only act on the progenitor T cells. They have no action on these killer cells, even though, as you can imagine, they are important for the killing of cancer cells. So how can we come up with a new strategy to harness the power of these killer cells and utilize them to bring the immunotherapy to a higher response rate? It remains as a big challenge in the field. So in my group, we discovered that when the T cells become terminally exhausted, they upregulate interleukin-10 receptor on the surface. So making these specific cells can respond very well to the cytokine called interleukin-10. So, and we further discovered that interleukin-10 can actually enhance the metabolism of these terminally exhausted cells, specifically enhance their oxidative phosphorylation or oxyphos. As a result, interleukin-10 intervention can substantially enhance both cytotoxicities and the proliferation of these terminally exhausted cells, or called reinvigorate T cells. Now, with these cells, they can continue to kill cancer cells way more efficiently and for much longer time. And this leading to enhance the response rate from 10% to 90% in one of the combination therapies. And finally, as I mentioned, we are also developing new chemical synthetic approach to modify the existing immunotherapeutic drugs. So here we develop a reversible chemical masking approach to mask the immune drugs. We call the switchable immune therapeutics or immune drugs. Once you inject this switchable drug to the systemic circulation of a patient, they remain as a switch off temporary once they are in the circulation or in the healthy tissues, causing no harm or no damage to the healthy tissues. Once they reach the tumor tissue, this chemical masking can be specifically removed in response to the tumor-specific stimuli, such as high reducing environment and a low pH, and then liberate the activities of this drug, and they can specifically activate the immune response in the tumor to control the tumors through these anti-tumor immunities. Although I'm talking to you about 3 different research programs in my lab, but we never regarded this research program as a separated different approach. We think actually, instead, we think these research programs are highly interconnected. For example, we are going to explore some of the connections among these directions, such as how the mechanical properties may impact the metabolism or vice versa. So this is my future research plan to really understand the connection of each of these domains in the next few years. So with that, I would like to stop And I really want to thank my formal trainings and current members. My previous postdoc, Yu Gangguo, Yu Qing, Zhao Yu, and Simon, so they are all either become professor or postdocs. So one of the postdoc, Yu Gang, is already currently a professor in Zhejiang University in China. And some of my former PhD students, they are now continue their postdoc training in prestigious universities, including MIT and ETH Zurich. And this is my current group. And we are keep exploring this multidimensional approach, immunoengineering approach. And also thank my formal trainings, including master, bachelor, and also some internship students. And also I want to thank the support from the EPFL, many of the offices and the core facilities. And also I had amazing collaborators in the past, including those in EPFL in Switzerland or in other countries. They all provide dramatic help in various projects. And I want to thank my funding support from various funding agencies and also the investment for my startup company to further explore these opportunities in the clinic. Thank you for your attention. I'll be happy to answer your questions.
Thank you very much for a very interesting talk. We have a few minutes for questions. Who would like to start?
Oh, I can ask a very general question because this is not my field, but I do have some curiosity about that. So this very nice talk. My question is about, when you're using for instance, the Stephen interference to really target on the cancer cell, and how could you actually differentiate cancer cell or from the other normal cells? So it's probably also applied to the other method you're going to attack the problem.
Yeah, this is a very good question. So I didn't have time to talk about the details. So first of all, I mentioned that cancer cells, they are oftentimes softer than normal cells. And we identify the reason is mainly because of the upregulated cholesterol as a lipid in the membrane in the cancer tissues or cancer cells. So compared to normal cells, they have more cholesterol in the membrane. So the way we stiffen the cancer cells, we use a drug called methyl beta cyclodextrin to specifically deplete the membrane cholesterols in these cancer cells because they express more cholesterol on the surface. Therefore, we can stiffen these cancer cells more than the normal cells. So there are some specificities. So in the future, we are also working on some of the delivery systems, for example, nanoparticles that can allow us to more specifically stiffen the cancer cells as the other cells in the tumor microenvironment.
Okay. Thank you.
Yeah. Who would like to? Yeah, Nicolas.
Dr. Tang, thank you very much. This was a very nice presentation of the field. I do work in this area, and I must admit that you gave us a wonderful introduction into immunotherapy and immunoengineering, and it took you about 10 to 11 minutes. And you very, very briefly mentioned some of the areas where you're working, and you were more concerned about telling us that your students went to MIT and you have so much money and so on. This is an evaluation of your work. And I take it like I did not learn anything from you today about specific projects, because you spend a lot of time telling us about what is important in the field, but this evaluation should be about what you have done. Am I wrong? Did I misunderstand what you told me? I mean, this looked more like a presentation to graduate students to come and work in your lab rather than what you have done.
Sure. This, I see this as a very general talk to the general audience, right? Including anyone, not necessarily even scientists, because we have 20,000-30,000 people that can freely reach to this iCANX talk. So I want to design my talk that can be easily accessible to anyone, no matter what you are working on, no matter you are in the field, no matter you are a scientist or not. So that's why I only give very high level overview of my research and my, of course, my accomplishments for the evaluation of the committee for this award. I didn't try to give too much details of the research itself, because I have already submit my document as an application, the written document as an application to this award, which should be give enough information to the committee to evaluate my previous research in details. So this is the purpose of my talk.
So we are almost running out of time. So just to give you one last opportunity, in 30 seconds, what has been the most important achievement from your lab?
So the most important achievement is to looking at the immunity disease interactions from unconventional dimensions and understand this mechanical interaction and even utilize this interaction to design next generation immunotherapy that can potentially benefit cancer patients.
Okay, thank you very much. So, well, thank you for your contribution and your talk. Let's move on to the next speaker, Wenzhuo.
Thank you very much.
From Purdue University. Yeah, who will be talking about Tellurene electronics.
Hello, everybody. Good morning, good afternoon, and good evening, depending where you are. I want to thank the committee for giving me this opportunity to present our research. So in the next 15 minutes or so, I'm going to share with you our recent progress in Tellurene material, emerging 2D material developed in our group. So this year marks the 75th anniversary of the invention of the transistor. And the scaling of the silicon CMOS technology has been increasingly challenged during the past few years because the gate electrostatics of the device demand a very aggressive reduction in channel thickness to preserve the desired performance. The ultimate channel thickness for a field effect transistor in the foreseeable future is probably potentially in the sub-1 nanometer range. However, that has been not readily accessible for any three-dimensional semiconducting crystals because of the increased scattering of charge carriers at the channel to dielectric interfaces. So this leads to severe mobility degradation. Future scaling or more may require thin nanosheet transistor. We have seen that development from the leading industry like Samsung on TSMC. And in those development directions, 2D materials are considered as ideal candidates. So over the past decade, 2D material-based field effect transistors have shown great potential in achieving many wonderful performance like room temperature subthreshold, harmonic subthreshold for low power dissipation, and also very good immunity to short channel effects. And in the very recent development, for example, in the IEDM meeting this week, the leading manufacturers in semiconductor industry like TSMC, Samsung, Intel, they demonstrate their most recent progress in incorporating 2D materials in the back end for emergent devices, and also they include 2D material into their roadmap. Despite all of these exciting progress and the unique properties of 2D materials, there are still significant roadblocks that against from realizing the existing 2D materials potential for applications. So in my opinion, okay, I think a suitable candidate material platform should have at least a reasonable band gap so that we can have good sufficient on-off ratio for low power operations. And the material system should also be L-stable so that we can really implement them for real applications. And the material system, it should also have a high and near-symmetric carrying mobility for both electron and holes so that we can develop complementary devices based on that material system. And eventually, I think this is also very important, but largely overlooked in many of the ongoing 2D material research development is that the material should also be produced at a very large scale with minimal requirement on substrate. So to this end, Tellurene turned out to be a potentially competitive and interesting candidate to fulfill those requirements. So Tellurene is a group 6 narrowband gap p-type semiconductor, and it has very unique one-dimensional van der Waals crystal structure. So in the crystal structure of Tellurene, all the Tellurene atoms were bonded covalently along those chiral chains. And all of those chiral chains, like DNA molecules, they were bonded through a much weaker interaction, okay? And because of this structure, it has a broken spatial inversion symmetry, and that lattice with the high atomic number gave rise to the strong raspberry-like spin orbital interaction, a camelback electronic structure at the edge of the valence band, and also a radial spin textures. And because of this intriguing structure, tellurium has a small effective masses and also high mobilities. Therefore, early studies in like 1960s to 1970s intensively explored the use of evaporated tellurium thin film for high-performance field effect transistors. And since then, there are a lot of progress made towards increasing the grain size of the evaporated film to reduce the boundary scattering and increase the mobility. And very recently, thin tellurium devices have also been developed using advanced growth methods like sputtering, and also with further improvement to device yields. And also another interesting point is the earliest study on surface quantum states is actually in bulk tellurium, dates back to early 1970s by the Nobel laureate von Klinsin, who later discovered quantum Hall effect in silicon MOSFET in 1980s. But he actually started trying to explore that effect in tellurium. Despite these superior electrical properties of tellurium for advanced technologies, in the bulk or thin film format, the tellurium has a relatively small band gap, and that poses a potential challenge to effectively shut off the transistor with a low, and therefore it has a low on-off ratio compared to stable or silicon transistors. And this issue could be potentially mitigated by significantly increased band gap if we can aggressively reduce the dimension of the tellurium thin film down to the atomic two-dimensional limit. And tellurium, there has been a lot of interesting and exciting research trying to explore, grow different morphologies of tellurium nanostructures. However, during the past 2 decades or so, all of those efforts ended up with one-dimensional format like nanowire, nanotube, because of this highly anisotropic structure of tellurium. And much less is known about the 2D form of tellurium and also related properties. This current chain structure also indicates it's very challenging to try to peel off atomically thin flakes with the mechanical exfoliation method. Recently, a Van Wolf's epitaxial growth method was developed to grow tellurium nanoplates with a thickness around 30 nanometers on mica substrate. And in this structure, the atomic chain is oriented out of plane. And you can see that there are a lot of edge roughness indicating the existence of numerous defects. Progress has also been made to grow two-dimensional tellurium thin films with MBE method on graphene substrate. However, these graphene substrates poses challenges to perform subsequent transport measurement, and it requires very complicated transfer method to detach this monolayer T film from the substrate. Has also been other strategies to obtain polycrystalline T film, including PLD, pulse laser deposition, magnetron sputtering, and liquid exfoliation. And large area, single crystal, atomically thin tellurium samples is still missing, especially by using substrate agnostic method. So we actually have a serendipitous finding. When I just started my group back in 2016 at Purdue, we tried to grow tellurium nanowires following the procedures reported in the literature. And at one time, we accidentally found among the ocean of tellurium nanowires, we found this nano ribbon. At that time, this ribbon is only around 100 nanometers wide. And it inspired us to explore more why this happens, because this has never been reported before. And since then, we were able to expand that growth and transform that one-dimensional growth into a fully two-dimensional growth, getting atomically thin tellurium flakes with controlled thickness and very large lateral dimensions ranging from tens of microns to even hundreds of microns, using an accurate solution method without using any substrate. So in this case, we can prepare these tellurium flakes in water solution and transfer them onto any substrate afterwards. And the TEM analysis show that the obtained flakes possess a very clear chiral chain structure of the tellurium. So we can we spend more efforts to try and understand the fundamental manufacturing of synthetic science, synthesis science here, and by modulating the parameters for synthesis. There are many important condition parameters here, like the concentration of the precursors, and also the time, and also the property of the capping agent. In this case, we use a PVP, which is a very common capping agent for chemical synthesis. And we can also achieve very good control over the thickness for the synthetic tellurine samples here from 3 layers, 2 layers down to 1 layer. And also, we were lucky to get a US patent for this technology. And with such a method to produce a large quantity of high quality two-dimensional TE crystals, we were able to probe the fundamental electrical properties of these materials. And our measurements show that these high quality single crystal 2D TE devices exhibit very high home mobility and room temperature without any advanced device engineering. It already achieved 700 or even 1,000 mobility, and that is very good and comparable to like black phosphorus, but much stable than black phosphorus. And this device also shows very high on-off ratio, around 10 to 5th, and with an on-current density larger than 300 milliampere per millimeter. By taking advantage of some device engineering like channel scaling down to short channel and also with high K ALD dielectrics, we can drastically improve the device performance and achieve a very high current density up to about 1 ampere per millimeter. And that was among the highest for any two-dimensional field effect transistors. So we also try to explore, okay, whether we can really scale up the production for Tellurene using this method. And we demonstrate and we probe the reliability and repeatability of these materials. And it turns out that the obtained samples show very consistent performance in terms of the field effect transistor devices, and also show a very strong dependence. The performance of the transistor show very strong dependence on the material thickness, and that gives us some avenue to control the device properties through the manufacturing process. So before that, we need to understand the process structure property relation. So right now we are using autoclaves and hydrothermal synthesis, and the volume of autoclave is small, like 50 milliliter standard ones. But the literature shows that we can potentially use even larger autoclaves, and the industry has been using this hydrothermal process at a very much larger volume. Of course, it's not trivial to simply just scale from what we have been doing in the lab to those industrial settings. However, that also provides a lot of interesting opportunity for us to explore and study. So in the process, we, because of the time, the length of the period of the experiments, it's very challenging for us to generate a large amount of data. So we usually have very limited set of experiment data. So we asked a question from the beginning: can we learn from this limited experiment data and generate some useful knowledge to guide and optimize our manufacturing outcomes for Tellurene synthesis? And interestingly, we use some statistic data approaches, and we generate interpretable knowledge that can be incorporated into the machine learning models for us to design the experiment and give us some unexpected optimal points. And we validate those conditions, and the result was surprisingly good for us to get a control over the average thickness of the Tellurene crystals from one batch, and more importantly, standard deviation of the thickness, because for 2D materials, if you change the thickness by one layer, the property will be totally different. So it's very important for us to control the standard deviation as well. And as I mentioned before, in order to get a complementary device with high performance, you need to have both NMOS and PMOS devices with near symmetric performance. And therefore, instead of our silicon technology, we need a very good controllable doping technique. However, that has been challenging for most 2D material technologies. For Tellurene field effect transistors, we can achieve very high drive current and field effect mobility for N-type Tellurene devices with very symmetric performance, as you can see here, to the native P-type devices. Then we further demonstrate the first Tellurene CMOS device with a very good, quite good, reasonably good gain performance. And with such material capability, we further explored for the first time the microwave performance of Tellurene MOSFET, and the device showed much better performance than molybdenum MOSFET and comparable to black phosphorus devices, but this device is much more stable. This also allows us to explore very intriguing topological nature of electrons in Tellurene conduction band. For example, it allows us to achieve gate-tunable topologic states. So in most of the direct and wide node materials, they don't have a band gap. So essentially, most of those materials are semi-metals. Therefore, it has little use for electronics or optoelectronics. You cannot tune those states through electric gate. if we can expand wire metal into semiconductors, that could enable unprecedented new platforms for studying intriguing quantum phenomena. So we reported the first experimental observation of wire females in a semiconducting Tellurene. And this is very exciting, and we have many ongoing work based on this work. And our efforts also received interest from the industry. For example, 26, that's the largest vertical integrated supplier of Tellurene-based products in the world. They approached us and they sent us some raw samples from their Tellurene mines in Philippines. And we used their raw samples and were successful to grow very high quality Tellurene samples in our lab. And we have ongoing collaboration with 26 and Coherent to develop Tellurene technologies for various applications. So in addition to electronics, there are also many other opportunities for the emerging Tellurene system, and we are very excited about this. For example, because of the tunable band gap in the visible to infrared range, Tellurene turns out to be a very good IR detector material. And it also can be easily incorporated into photonic circuits for modulation for sensor application. And Tellurene itself is actually a very good thermoelectric property. When you reduce the atomic when you reduce its dimension to atomic thickness, it turns out to be an even better thermoelectric property material. And something I don't have time spent here and is because of the chain structure, you can easily induce phase transition in two-dimensional Tellurene through mechanical strings, through electrical bias, or even just simply heating. And very recently, we utilized Tellurene to develop wearable sensors for monitoring sweat and also incorporate it into quantum circuits for topological quantum computing applications. And there are also more and more exciting opportunities I'm really excited about. So based on that serendipitous finding 6 years ago, my lab is now primarily focused on how we can precisely produce Tellurene materials with controlled property, controlled defects levels, controlled dimension morphology, and how we can integrate and incorporate those obtained Tellurene materials through emergent and traditional manufacturing process, for example, rotary methods, 3D printing, and incorporate them into useful products for the benefits of the human society. So with that, I'd like to thank my former and current group members, our collaborators, and also our funding agencies, and also thank you for your attention. I'll be happy to answer your questions. Thank you.
Yeah, thank you very much for your contribution. We have a few minutes for questions. Who would like to start?
Let me maybe start.
Okay.
A general question about Tellurene. It seems to receive very little attention. Altogether, I see less than 200 papers published over years, in spite lots of papers on other 2D materials, including elemental ones here. How do you explain it? Why is the community showing so moderate interest? Let's put it this way.
That's a very good question and also valuable. So I think one of the main reasons is still in the challenge in obtaining high quality two-dimensional Tellurene crystals. So actually we have seen actually many groups approached us and we actually been trying to grow the material. Some group from UC Berkeley, MIT, and also from Singapore and other areas of the world. They have been successful in growing smaller sizes of Tellurene. We shared our information with them. I think there might still be some lurking factors, which is also the reason why we want to bring in an analytic approach like machine learning, interpretable machine learning, to understand better the system. So even in our lab, I think due to those lurking factors in the entire synthetic process, our repeatability is getting better, but not so good actually. So I think that's probably one of the main challenges for other groups to pick up the progress and follow and pick up the momentum. So I think I'm really interested and I really want to promote this material, and I want to share that with the other researchers. So, but I think, in my opinion, that's the main reason. Yeah.
Two minor technical questions. It looks like you are getting still not a single layer, but few layer Tellurene. Am I right?
Yes. Yes. Yeah. And the optimum performance for field diffractions comes from 5 to 10 nanometer Tellurene instead of monolayer. Yeah.
Right. And the second question then is here. I know there is a high mobility of tellurine, but if you compare it to other 2D semiconductors here, what are the advantages? And if you see that with a few layers, it will be even more challenging to make reproducible devices and controllable technology.
Very good question. So actually, we put a benchmark chart here. This was done actually more than 3 years ago, and at that time we measured mobility from tellurine samples with thickness across a large range from monolayer to tens of nanometers, and we benchmarked that against all the reported values from the then two-dimensional p-type semiconductors. And you can see that, yes, if we compare to the best reported values, our tellurine materials show comparable, sometimes better, but some comparable performance. I think the largest advantage here is that we can produce this material without using any substrate in water at a large scale. And then we can control the thickness and transfer them onto any other substrate. So I think here, a point I want to make is that we are now trying to replace silicon. I don't think that's going to happen. I think what we can offer here is probably some augmented capability to supplement silicon devices. And in that sense, I think it's especially for the back-end integration, it's very important for the material platform to be substrate agnostic, so that you can easily integrate them into existing platform technologies without rebuilding everything from the start. So I think that's the biggest advantage. Another thing is for tellurine, it's much more stable than most other p-type two-dimensional semiconductors. Black phosphorus is notoriously known for LE stability, and many others also are not stable. But tellurine, in our case, well, if we don't put any device engineering like encapsulation, it can already remain stable for over 2 months in the air, in the humid summers here at the West Africa. And if we put encapsulation to them, it will be even more stable. So I think those are two main advantages compared to the other technologies.
Thank you.
Thank you.
Thank you very much. I see Lanfu has also maybe one short question considering the time.
Yes, thank you. I just want to quickly understand, you talk about scalability and all this. How can you actually make a position accurately when you really incorporate it into integration with other devices and all this, because they're all randomly dispersed in water?
Yes, it's very good. So yes, it's randomly dispersed in water, but we can realize, we can take advantage of methods like LB assembly and those chemical assembly methods. So we can determine, in this figure, we show deterministic transfer of tellurine flakes obtained from the solution to desired location on the silicon substrate. And then once you have that, you will be able to build the circuits upon that. So that's a very good question. But that requires the precision in both steps, the synthesis steps and the post-assembly steps. Yeah. Thank you.
Okay, thank you. And then
I think there's one more question. Yes, one more question from Dr. Peppers.
Yeah, one more short question from Nicolas, and then we go to the next speaker.
Well, I don't want to take too much time here, but your answer to Dr. Gogoji's question was not very satisfactory to me, because I've been following the literature and there are very, very positive comments about tellurines. Okay, so I really, there must be another reason why not so many people are working with it. It's probably that some other structures are better, or it's probably that they are more expensive and so on. Just leave it over here. We don't have time to discuss it now. But
thank you.
When you look at the literature, it says very positive things about tellurines, okay?
Yeah, I think I will think about that, and maybe I can get back to you with my more formulated response. Thank you.
Well, thank you. Unfortunately, we have to stop this very lively discussion and go on to our next finalist. This is Chaoji CHEN from Wuhan University, who will be talking about developing low-carbon functional materials.
Chaoji, you mute. Sorry. Yeah. Hello, everyone. This is Chaoji CHEN from Wuhan University. It's my pleasure to share with all of you on the developing of low-carbon functional materials from lignocellulosic biomass. We know that there is woody biomass is abundant and everywhere. It's reported that there are 3 trillion trees. Each of us can have 400 trees. More importantly, there's abundant agricultural and forestry biomass waste. Most of them, however, are directly abundant or burned, causing great environmental pollution and increasing carbon emissions. Therefore, high value-add utilization of agricultural and forestry biomass waste is one important way to achieve the new carbon neutrality goal. Before talking about how to use this material, let's look at its hierarchical structure. Wood as a typical woody biomass, for example, it has hierarchical structure with the cell structure as the unit structure. This cell wall contains a multi-level fabric structure. For example, the microfabric bundle can be further divided into elementary fabric, and even down to this molecular chain with rich hydrogen bonds. From chemical point of view, it is mainly comprised of cellular, hemicellular, and lignin. There are 2 general ways to use this woody biomass. One is called bottom-up. We need to defibrillate the biomass into these nanoscale building blocks and then assemble it into box-scale functional materials. Unlike this bottom-up approach, the top-down approach can directly turn this woody biomass into bulk functional materials without breaking down its hierarchical structure. Therefore, it can have some unique properties. Regarding these top-down modification strategies, we contribute to several cell wall engineering strategies. We summarize it into 3 categories. For example, the chemical composition engineering of the cell wall. We can take out some components and even functional groups from the cell wall to engineer its structure, or we can add additional components to this cell wall. For example, polymer or nanoparticles. And the second category, we can engineer the spatial structure of the cell wall. For example, we can close the cell, we can ring the cell wall, or we can engineer the surface interfacial structures. For example, we can grab a functional group to the cell wall. In this case, we can modify its surface properties. With such a diverse tunability of the structure, we can turn its properties as well. For example, we can achieve pore structure engineering, pore size porosity, or even the pore tortuosity, or the surface interface structure. For example, the surface charge density, wettability, or even the crystalline structure of the lignocellulose biomass. For example, amorphous or less amorphous, or even down to the molecular scales of the cell wall structure. In the past few years, with such rich modification strategies, we developed a series of low carbon functional materials with potential application in lightweight structural materials, biodegradable plastics, and buildings, and functional devices, and energy and water. Due to the limited time, I will give a few examples on these lightweight structural materials and biodegradable bioplastics. First, let's look at how we use this woody biomass to make lignocellulosic lightweight structural materials. As we know, steel widely used structural materials, but the production always involve a high temperature process with heavy carbon emission. Therefore, it's less sustainable. Wood is more abundant and renewable, and also it is zero greenhouse gas emission. Therefore, it's a more sustainable and greener structural materials. However, it faces two major challenges. One is the moderate mechanical performance, and the second is the poor formability, which may make it less competitive to steel in advanced engineering fields. 4 years ago, we invented a two-step manufacturing process by combining the partial densification and densification process. We can achieve like 80% record high reduction in the volume thickness. In this way, we can achieve 600 megapart, as strong as steel, but is 6 times lighter than common steel. Therefore, it is specific strengths outperforms like steel and other structural materials like metals and alloys. From this morphology view, we can see these open cells in the natural wood can be completely closed in this densified wood without breaking its cell wall structure. At a finer scale, you can see this nanofiber alignment can be well maintained. Therefore, it delivers 10 times improved mechanical strength in tensile strength, and also is superior to many artificial polymers, and the ballistic resistance improved 10 times as well. As can be seen in the video, the laminate XY direction of the densified wood can even block this bullet. There is this multi-scale strengthening mechanism. From the box scale, is a dense structure with less defect. From this micro scale, this intertwined microfibers can consume more energy when you break this structure. Also, at the nanoscales, this aligned nanofiber have the maximum interface. Therefore, it can consume more energy. At the molecular scales, this hydrogen bond can be break and reform in this repeating way. Therefore, it can consume more energy. We can see this a promising lightweight yet strong structural materials. But in some applications, we need a good formability as well. We keep thinking about how about the formability of this material or the wood biomass. Fortunately, last year we have a breakthrough. We make wood moldable via this cell wall wrinkling strategy. By this water shock process, we can ring the cell walls and make this big cell core vessel partially open, while the small cell core fiber closed. Therefore, this vessel can be further compressed or stretched, while this closed fiber can connect this partially open vessel. Therefore, our moldable wood can be as moldable, foldable as paper, but is much stronger than paper. Therefore, we can make various 3D shaped structures. And more importantly, we not only make this wood moldable, but make it 6 times stronger than the natural wood. It's also 5 times stronger than aluminum alloy in the specific strengths. Also, we can achieve a very scalable manufacturing. For example, we can make 1 meter long wood honeycomb, which is even stronger than the alloy honeycomb core. It can support a 1.5 ton SUV without breaking, and this 1,500 times of its cell weight. Professor Yuanyang from Yale University helped us perform this life cycle assessment. Compared with aluminum alloy, our material performs much better. The low value means the low environmental impact. For example, the global warming potential. Our material is a few times lower than this aluminum alloy. Compared with the aluminum alloy honeycomb core, our material has a better mechanical strength, low cost, and is more sustainable. The second part, I would like to share with you how we make lignocellulosic bioplastic from woody biomass. We know that in modern society, the production of plastic is increasing every year, and most of them is disposed to the environment, and some part even go to the ocean and turns into microplastics and go to the food chain and even go to the human body, causing severe health concern. Therefore, many nations are banning the non-biodegradable plastics. However, currently, the global market size for bioplastic is still very small, less than 1%. That means that the future market size is huge and means a huge opportunity. There are some commercial bioplastic products, for example, PLA and some bio-based thermal plastics, and most of them has a lower strength and lower thermal stability compared with the petrochemical-based products. And most source materials are mainly from food resources, which may lead to the competition of food resources with human. We have another choice. There is non-food lignocellulosic biomass, which is renewable, abundant, and more importantly, they are naturally biodegradable. For example, wood can be attacked by the wood-eating insect, wood decay by fungi. These are evidence for wood's biodegradability. Based on this consideration, we developed an all-component lignocellulosic bioplastics through these lignin regeneration strategies. Unlike the palm industry, lignin is treated as a production waste. In our process, we dissolve the lignin and then regenerate it to reinforce this cellular fibril network. In this way, we can achieve a better mechanical strength and better water stability. And this material is biodegradable. It can biodegrade and come back to the carbon cycle of nature. Also, we can achieve large scale production. Here we take use of this DES to break the beta oxygen 4 bond, which break the hydrogen bond between cellular fibers and dissolve lignin. The one benefit of the lignin regeneration strategy is that the regenerative lignin can serve as the glue to bond these cellular fibrils and chains. In this way, we can achieve 7 times higher mechanical strength than this cellular film without regenerative lignin. And this value outperforms many conventional plastics. The second benefit is the better water stability, because the regenerative lignin can protect this cellular fibrils. Therefore, it can improve the water resistance of these materials. For example, the water absorption value is much lower than this cellular film. And this material is completely biodegradable. For example, when we bury this material under soil, it can be degraded for up to 3 months, and exposed to the outer environment, it can be degraded after 5 months. Also, Professor Yuan Yang from Yale University helped us perform this life cycle assessment, compared with the non-biodegradable plastic product. Our material performs better. The low value means the better. And even compared to these biodegradable plastics, such as PHA, PLA, and so on, our material performs better as well. We are at an age of biomass, although we face some challenges. For example, the high energy water consumption, performance is hard to compete with existing products, or most of these products are in the lab, or we are not sure whether these are truly sustainable. But with these challenges addressed, we are expecting a new age of biomass. I would like to thank my supervisor, Professor Lianbin Hu, my postdoc supervisor and collaborators. I thank my group members in Wuhan University, thanks the funding agencies, and thanks Wuhan University. Thank you all.
Well, thank you very much. We have a couple of minutes for a short discussion. Who would like to start?
I can start again.
Okay.
Very interesting talk, and clearly nanocellulose has been receiving a lot of attention, and Lianbin, who your supervisor, gave a brilliant talk at iCANX about it. I'm wondering, I'm just trying to kind of differentiate which part of this work is like your original work and how is it different from what Lianbin has been doing and is doing in the field. Can you like briefly summarize your contribution?
Yeah, thanks, Professor Gogosi. Yeah, actually, most of these works were done when I was a postdoc in Professor Lianbin Hu's group, and for most of these works, I'm the first also. I did the experiments and write the manuscript and so on. But just last year, I came back to Wuhan University and I built my own lab. Therefore, yeah, most works are done during my postdoc research in Maryland.
Okay, thanks for clarifying. Mm-hmm.
Yeah, thank you.
Yeah. So maybe you could say a little bit what problems you want to solve next. Your lab is very young. What are now the big problems you're going to solve in the coming years?
Yeah. Actually, there are mainly two aspects. One is that I would like to develop some greener synthesis process, and also I would like to develop some life cycle assessment. Also, most studies are still in the lab scale. I would like to make some products in the market to truly benefit human society.
And why do you think this is the best approach? I mean, you give a very impressive introduction, but what about other methods, other approaches? For instance, in this context, one can also read and hear a lot about simply improving recycling to solve these kind of problems. So how does your approach complement or maybe help to make this planet a better place via your approach? What is the big difference here?
As our lab, my lab is very young, so for many some approaches we are still under developing. For example, we try to take advantage of the bacteria to modify this wood cell, and in this case we can use less chemicals and less energy. This one example, we want to take advantage of the bacteria biological process with this physical and chemical process combined together to get a greener and less energy intensive process. And also another
Sorry
direction
for interrupting. I was more like aiming at when you have these kind of biological processes that put a lot of pressure on the natural resources of our planet, we have a shortage of lands. When we start to plant trees for this process, we lose biodiversity. Even in many places, water to grow plants and biomass is already not readily available. So I can imagine we cannot build entire cities, as you seem to suggest on this picture, using this method. We don't have enough space, resources, right?
Yeah, actually, regarding this biomass resources, my lab is also focusing on using this biomass waste. That means we do not need to use the good, the high quality biomass like the wood product. We just need we can use the straw and the wood powder in the wood industry is treated as waste. And also we want to do some research on this paper packaging waste and so on. Yeah. Our lab is also focusing on using this biomass waste instead of good quality biomass.
Yeah. Okay, thank you very much. Well,
Yeah,
this was the
thank you.
last speaker for the 5-minute coffee break. So now we have a 5-minute break, and then we will continue. See you soon.
Awesome.
不再是奇迹，不再是幻想，此刻真感觉全世界对我鼓掌，不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can, I can， 没有什么可以阻挡心中无限的力量。I can, I can， 你也能够像我一样飞越最高山岗。I can, I can。没有什么可以阻挡心中无限的力量。I can, I can， 你也能够像我一样飞越最高山岗。创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can, I can， 没有什么可以阻挡心中无限的力量。I can, I can。能够像我一样飞越最高山岗。I can, I can， 没有什么可以阻挡心中无限的力量。 不再是奇迹，不再是幻想，此刻真感觉全世界为我鼓掌，不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can, I can， 没有什么可以阻挡心中无限的力量。I can, I can， 你也能够像我一样飞越最高山岗。I can, I can， 没有什么可以阻挡心中无限的力量。I can, I can， 你也能够像我一样飞越最高山岗。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can, I can， 没有什么可以阻挡心中无限的力量。I can, I can， 你也能够。
Falling 5 parts. First, let's start with the research background. Nowadays, carbon neutrality is one of the most important goals for the global environment and economic development. For energy and environmental issues, controlling the carbon footprint becomes a critical challenge. To achieve this goal, reducing carbon emissions and developing the sustainable energy are the key research directions. Especially carbon dioxide reductions, fuel cells, and biodiesel generations are the most important technological solutions. And these technologies are all strongly rely on advanced and efficient catalysts. To realize their practical applications, the key challenge is to find efficient and stable catalysts. Due to the high electroactivity and low cost, atomic catalysts have become the most promising candidates among emerging materials. Therefore, the rational design of this candidate is too significant for achieving the carbon neutrality. Since 2003, scientists already discovered the unique electroactivity of atomic metal atoms. In 2011, the first single atomic catalyst has been synthesized by Professor Changyong and his group. Since then, atomic catalyst has become the most frontier research topic. Compared to the conventional noble metal catalyst, atomic catalysts have several key advantages, including the high electroactivity, controllable loadings, and low cost. And these advantages enable their broad application in sustainable energy systems. The atomic dispersion of the metal atoms will significantly change their electronic structures, and this usually induces their unique electroactivity in the future. However, due to the ultra-large surface energy of the single atom, the aggregation problems becomes a challenge. To overcome these difficulties, the appropriate support materials is highly important to stabilize the single metal atoms. Carbon materials are the most promising ones among all investigated supporting materials. And this is because they usually have the high electrical conductivity and stability in different catalysis environments. Graphene is one of the most promising carbon support materials for this atomic catalyst system. First of all, it has a large surface area with a naturally ordered power structure. And this supplies a good coordination environment to stabilize more single metal atoms. Meanwhile, it also shows a high electrical conductivity to guarantee efficient electron transfers. Its remarkable chemical stability enables its application in different electrochemical environments. Most importantly, the flexible carbon bonding types in graphene can supply valuable references for designing atomic catalysts on the other carbon materials in the future. So, based on graphene, we have carried out serious researches on atomic catalysts. In general, the unclear valence states of the single metal atoms are the significant challenges. This also limits the synthesis of the zero-valence atomic catalyst. To address this difficulty, we propose redox barrier as a new model to quantify electron exchange and transfer capability. Based on this model, we have globally searched all transition metal and rare earth metal to compare their electroactivity, electronegativity, and stability on the graphene support. With this model, we have also provided energetic mapping for describing the side-to-side charge transfer in two directions. Meanwhile, the redox barrier model also supplies a method to accumulate the rich parameters of an atomic catalyst. And these parameters can further compatibly integrate our following machine learning in predict and screen out the new candidates. Based on these preliminary efforts, we have identified nickel, platinum, palladium, and cobalt are the most promising candidates for zero-valence atomic catalysts. Then we further explore their application in sustainable energy system. Hydrogen evolution reaction, HER, is the most promising method to efficiently generate hydrogen energy. For this reaction, conventional DFT usually compares the proton binding energies as the only criteria. But we have extended the criteria with the absorption energies protons and desorption energies of hydrogen molecules. Compared to the transition metal, lanthanide-based atomic catalysts actually show high electroactivity. We have screened out the Sumerian and European atomic catalysts with great potential for HER. Meanwhile, we also identified that the carbon alkyl chain on the graphene is the active site for the HER rather than the metal sites. Based on these efforts, we established and developed the first principal machine learning methods for atomic catalyst design for the first time. The parameterization database is based on redox barrier model and the fundamental physical-chemical properties. With this strategy, we have predicted the proton binding energies, models, and fundamental physical-chemical trends for the all-studied atomic catalyst. The prediction showed a highly similar trend to the traditional DFT calculation results. And this confirms that first principle machine learning methods can be a promising investigation strategy to develop the novel electrocatalyst. Beyond the single metal atomic catalyst, the dual atomic catalyst DAC will supply more possibilities. Introducing the second metal can enable more flexible modulations in the electroactivity. In most cases, the dual metal atoms need to be stabilized by additional bridging agent traditionally. And this is due to the strong repulsive force induced by the DD orbital coupling. To overcome the stability challenge, we propose introducing lanthanide metals can be a promising solutions. The FD coupling actually induces an electron cell balance effect to alleviate the strong repulsive force in the transition metal pairs. To find out the promising dual metal pairs for experimental synthesis consideration, we have investigated all the 968 combination possibilities between the transition metals and lanthanide metals. We have, as we expected, most transition metal pairs are not stable with large formation energies, especially for the heterocoupling between the different transition metal pairs. In comparison, the combination between the lanthanide and the transition metal show much improved stability. And this is the most stable selection for DACs. To further understand electronic modulation, we propose F-band center for the first time. The F-band center show the V-shaped valley trend, and the middle lanthanide metal show the lowest F-band center. Compared to the traditional D-band center, the F-band center is more sensitive to the second metal on the atomic catalyst. Due to the strong FD orbital coupling, the electron can be transferred from D to F orbital through the cell balance effect. And this effect can further optimize both electronic structure and thermodynamic stability. Beyond the transition metal and the lanthanide metals, many main groups of elements are also potential selection considerations. Then we further increase and these metal pairs to 2048 possibilities by considering the main group elements. Introducing these elements actually induced the SPDF orbital coupling effect possibilities, and these effects can further optimize stability and electroactivity. The main group elements can be effective separator to increase the metal loading. Meanwhile, they can also activate intrinsic electroactivate the carbon alkyl chain graphene through the PP coupling. Overall, the main group elements and lanthanide pairs are promising selections for DAC throughout the periodic table. Notably, we further apply self-validated first principle machine learning to predict their performances. The thermodynamic stability of a dual atomic catalyst can be predicted with a relatively high accuracy. In contrast, the p-band center, however, predictions show much lower accuracy. This is due to the evident electronic modulation induced by strong PP coupling as noise signals. These results suggest that orbital coupling will become a significant challenge for future machine learning predictions on electronic structures. Recently, we proposed applications of graphene support SAC in carbon dioxide reduction for the first time. Based on this platform, we established over 5,400 models to carry out a comprehensive study for carbon-1 pathways. We discovered the carbon dioxide absorption is highly related to the electron configuration of the d orbitals. Meanwhile, the energy mapping supplies a comprehensive understanding of the product selectivity. And most of transition metal SAC prefers the formation of the carbon monoxide, while the lanthanide SAC favors the formic acid generation. For the formation of a more complicated methanol and methane, transition metal SAC are difficult due to their high energy barriers of the hydrogenation process. However, these high energy barriers become much lower for lanthanide SAC, especially for praseodymium and promethanium. All active sites are energetically favored in methanol and methane generations. This work has confirmed that both thermodynamic and separation spatial factors are significant for carbon dioxide reduction for SAC systems. Meanwhile, we also investigate neighboring effects of this SAC. Interestingly, the initial process of a carbon dioxide absorption is more favored on carbon alkyl chain. However, the metal sites dominate the following reaction steps during the catalysis. This means that diffusion of the carbon dioxide among different active sites is the key factor to promote the reduction process. Moreover, introducing the neighboring effect can strongly promote accuracy of machine learning prediction in the future. And this work supplies important insights into the catalysis mechanism investigation for carbon dioxide reductions. Our theoretical investigation of graphene support atomic catalysis are also verified by experimental collaborations. Our collaborations with Professor Yuliang Li from Chinese Academy of Science successfully proved the remarkable performances of several graphene support SACs. These are consistent with our theoretical predictions. And based on these works, besides the graphene, we extend our research to other supports. On the nitrogen-doped carbon, we collaborate with the experimental group to synthesize iron-doped SAC. The 3D orbitals of the iron show strong electron exchange and transfer capability. The PD coupling effect between the iron and the carbon support leads to the electron distribution optimizations. In addition, we applied orbital peak modulation strategy to improve the overall kinetic rate of the oxygen reduction reactions. And then we move on to the oxide system. We stabilize the iridium single atom coupling the oxygen vacancy on the spinel oxide through the experiment. Due to the coupling, this electroactive region has been clearly characterized, and this enables the stable absorption of the key intermediates and maintain the valence states of the surface cobalt sites. And this electronic structure optimization guarantees the efficient oxygen evolution reaction in the acidic media. Besides SAC, we also successfully achieved the zinc and the lanthanide DAC with the Nankai University. And this DAC shows high performances for the syngas generation. The zinc and the lanthanide atoms are responsible for the active site for carbon reduction and hydrogen evolution reaction, respectively. By adjusting the ratio of these two metal sites, the components of the syngas can be modulated in a large range. And this work further reveals the great potential of lanthanide-based atomic catalysts in the future applications. Beyond atomic catalysis, atomic level modulation is also a significant tool to improve this electroactivity. In typical homogeneous electrocatalysis, we identify irregular deep and center change induced by the string effect. And this means the string effect may have the oversimplified in many words traditionally. To overcome this challenge, we propose a new parameter, surface atom density. And this parameter linear correlates the different high index physics with the surface energies and electroactivities. It can break through the limitations of elements and the morphologies which further extend to more catalysis processes and systems. And based on this work, we further visualize the atomic strain distribution in late transition metal nanoparticles. Different from the lattice strain, the surface atomic strain is a very interesting intrinsic feature of the nanoparticles. Their distribution and levels are determined by the both elements and the surface structures. Especially the surface steps and kink size with low coordination numbers show atomic compressive strain. And this size visualization technology are the key factors to improve the surface electroactivity predictions. And this work helps us establish the theoretical framework for studying the high index physics for different nanoparticles is very important. And then to summarize, first, we have proposed a novel Redox barrier model to quantify exchange and transfer capability for zero valence atomic catalysts on the graphite for future other system consideration. And based on this model, we further established the first principle machine learning method. And this method helped us identify suitable metal pairs for future dual atomic catalysts and trial atomic catalysts. We further the consideration that introduction about the lensline method is significant for the high electroactivity and stability. More importantly, we have screened out lensline-based SAC, a promising candidate for both hydrogen evolution and carbon dioxide reduction reactions. And this is due to the electro-optimization by the orbital coupling effect of the F bands. Besides atomic catalysts, we have proposed surface atom density as a new indicator to visualize surface atomic strain. And this is critical for us to understand electroactivity modulation in nanoparticles. In the future, we hope to realize the rational design of more atomic catalysts with high performances and inspire more research to contribute to the development of advanced energy system. In the end, I would like to thank my group members and found support from the different agencies for our research. This is the end of my talk today. Thank you all.
Thank you very much. Who would like to ask a question first?
I can go if no one else asks.
Yeah, Yuri? Okay.
Yeah. So basically, I have two questions. One is I'm still struggling a little bit to understand advantage of graphene relative to other 2D materials, including or just porous carbons, high surface area carbons for single atom catalyst. And the second question is, one of the key problems with single atom catalyst is basically clustering and degradation over time. Did you try to address this? So there are two questions here.
Thanks for Professor Yuri's questions. For the first questions, what I said, the graphene actually has the same advantage to the other 2D materials. The advantage is really, really important for computational efforts. Because once we focus on the carbon-based materials, we usually consider carbon clusters and amorphous carbon or diamond-like carbon systems. But however, that takes 300 or 400, 500 atoms. But we can't waste so many computational resources just for the load.
Got it. It's simply periodic structure, easier for computation.
So the graphene is have advantages for the different carbon bonding environment, like the carbon single bond, double bond, and triple bonds, and the mixtures in the one system. So this is with a very low computational loadings to build up the models. So this is the one. Actually, it has the same, almost the same or similar advantages and performances compared to the other carbon-based 2D materials, and also the like a graphene or defective graphene oxide graphenes. So this is the first answers. The second answers for the metal loadings, because they usually have the clustering effects, because their bulk materials, they are trying to the bulk materials is very important. So we are trying to separate that. So we need to use the support materials to hinder their clustering effects. So stop their to maintain their dispersive distributions. So we need to use the large power structures, such as graphene. So in overall consideration, we choose the graphene in theoretical modelings and also experimental synthesis. Thank you for the second questions.
Let me clarify a little bit here what I was looking for, Bolong. When you get, say, 2 atoms of metal, say platinum on graphene, when the process starts, when they work as a catalyst, over time, they tend to move together. That's why, for example, we embedded into vacancies on MXene that we use it here. So did you, in your calculation, address this issue or only catalytic ability here? Because this is a key thing that kills single atom catalysts over time.
Thanks very much.
Dynamics of basically single atoms on graphene.
Well understood. Thank you very much for your questions. In our calculation, we have already considered stability testing once we're building up the models for anchoring that metals, especially after the stability testing and computation checking. We will perform the MD testing round, so molecular dynamics rounds, because in theoretical and practical, the metal atoms anchored on that will also diffusing on the surface. This is due to the thermodynamic instability. We also consider about that. And theoretically, the natural powers easily stabilize the atoms, will suppress that migrations. So we still consider the graphene is for this reason. Okay. In the future, we will consider the other defective structure, also another prominent 2D materials like MXenes, because this is the accumulation for the graphene. We are trying to investigate it.
Okay, thank you. Well, for the sake of time, we have to move on, and I would like to, as a kind reminder for the other candidates, try to stay within 15 minutes, so we have 5 minutes time for discussion. Let's move on to the next speaker, Tongchao Liu from Argonne National Laboratory, and the talk will be about rational composition and structure designs for lithium-ion batteries.
Thank you for the kind introduction. I hope my presentation is showing well. Can you hear me?
Yes.
Okay, sounds good. Hello, everyone. It's a truly pleasure to have the opportunity to present my research here. Today, I'm going to talking about a little bit different topic that has not covered by the previous speakers. Okay, energy has been commonly considered as the top 5 problem in the next 50 years. And the current world is mainly powered by the fossil fuels, which unfortunately is irreversible and causes serious pollutions. To eliminate our dependence on the fossil fuels, we had to develop new energy technology urgently. Today, I would like to introduce a very powerful and clean energies, that is lithium-ion batteries. Lithium-ion batteries can power small devices and electric vehicles, which has greatly changed our life. A typical lithium-ion batteries is a device that can convert chemical energy into electron energies. Specifically, a lithium-ion battery contains 2 active materials, cathode and anode. During the battery operations, the lithium ion will shuttle from one side to another to complete a chemical conversion. At the same time, the electron will go through the output to have the energy transferred. So let's take the cell phone as an example. The lithium battery should have the following characteristics. High energy density means your cell phone can use for long hours. For the fast charging, you can imagine your cell phone will be fully charged within 1 minute, and then you can use for 1 day or 2. That will be perfect. The other characteristics included the promoted safety, the long battery cycle life, and the low cost. Although lithium battery has still a lot of success in many applications, it still faces many challenges. The first challenge is the underachieved energy density. Despite the battery energy density keeping increasing, it's still below the predicted trends in 2022. At the same time, the battery is facing the high cost constraint. In detail, the high battery cost is largely attributed to the cathode materials that contain some trace metals with skyrocketing price. Other challenge of lithium battery include the short cycle life and the safety concern. Especially the safety concern has been the primary anxiety that put the customer away from the electric vehicles. In our lab, we have dedicated to understanding their failure mechanism and develop new technology to unlock the higher energy density, to reduce cost, to extend the cycle life, and solve the safety. I'm very excited to introduce my contribution to this field in the following slides. Efforts to solve this challenge had to start with an understanding of what made the battery failures. In the previous studies, many mechanisms have been proposed. However, some mechanisms are phenomena at a certain scale, and sometimes they are debated with each other. So in my research, we developed a multi-scale characterizations ranging from different length scale and different time scale. This will cover the characterizations from the electron level to the particle level, and then to the single particle level, atomic levels. So on the right side, I will show you one example, the multi-scale structure diagnostic systems. With this system, we could diagnose the whole chain of battery, including the material synthesis, the battery cycling, and the post-analysis. So now I will show you how this system works. We select the lithium-rich layered cathode as a model system because it shows very high capacity and a faster capacity fittings. To understand its failure mechanism, we first using in-situ XRD to monitor the structure dynamic at the electron level. So here the in-situ XRD indicate the all diffraction peak shows a reversible peak shift without any new peak generations. This seems to suggest the structure evolution is reversible. However, this cannot explain why this lithium-rich cathode suffer from a very fast capacity fading and voltage fading. To further understand this abnormal phenomenon, we zoom in this O3 peak using the SIM-MCD. So now we found different stories. When the battery charged to 4.47 volt, we directly observed the structure degradation occurred, and this exactly matched with the oxygen release as reported previously. So the remaining question is, what drives this structure degradation occurred? We further down to the single particle level using in-situ BCDI, we were surprised to find the lithium-rich cathode suffer from severe lattice strain in every single cycles. And also, this lattice strain accumulation will reach the maximum at a 4.43 volt, and this is destructive enough to trigger the structure degradations. The following atomic level high-resolution TEM confirmed the lattice strain occurs at a 4.5 and also with the new spinel phase generations. Combine these multi-scale characterizations, we for the first time reveal lattice strain is the root cause of battery failures. And with this mechanism proposed, we can harmonize the previous theory and solve the chicken and egg issue in this battery theory. So since we have no lattice strain really damage the battery performance, it will be particularly important to develop some strategy to solve it. So as we know, lattice strain usually manifests as uneven lattice bending, twisting, and bendings. This together will trigger particle crack and accelerate the particle, the battery degradations. So in the below picture, I will show you how lattice strain damage these particles. When we look at this particle from outside, it seems very stable after long cycle, 100 cycles. However, when we zoom in this cross-section slides, we found a lot of particle cracking occurred. Frankly speaking, strategy to solve the lattice strain has not been available. So here we bring a brand new strain retardant strategies. In these strategies, we introduce a perovskite phase into the host materials. The perovskite is structure coherent with the host layer structure, but has much stable structural framework. On the left side, we I show you a high resolution TEM confirm we have successfully built up nano-sized plastic guide in these layer structures. And further, the in situ XRD indicate we can increase the operation voltage from 4.3 volt to 4.8 volt, which will result in the 20% capacity increase. More importantly, with this method, we can reduce the lattice stream by 70% and also extend the cycle life by 6 times. Actually, this is the best performance we have achieved for these materials. Another challenge for lithium battery is the high cost constraint. As I mentioned before, the high cost of battery is largely attributed to the skyrocketing price of traded metals, especially cobalt. So really reduce cobalt usage and searching for some alternative elements will be top priority for these cathode materials. To do so, we first understand the role of cobalt in these materials. We synthesize 3 comparable materials with different cobalt content and manganese content. Manganese was selected because its price is only 1% of cobalt. So by characterizing these materials, we found cobalt can suppress the lithium-nickel disorder. The lithium-nickel disorder is a common structural defect that will reduce the capacity. As a result, cobalt can increase the capacity of cathode materials. However, during the battery cycling, cobalt will aggravate the layer blending and the particle crackings, which will together accelerate the capacity fading. So clearly, cobalt is the double-edged sword for batteries. The following comparison between cobalt and manganese reveal manganese can be a potential substitution for cobalt because manganese can stabilize structure and also suppress the particle crackings. So a remaining challenge need to solve is the lithium-nickel disorder. So we studied this problem in a separate work. We found out the magnetic frustration is the root cause of lithium-nickel disorder. And cobalt as a non-magnetic ion can well suppress the lithium-nickel disorder. With this understanding, we propose a new cobalt-free cathode materials, NMX. So X can be any other elements has a function as a cobalt, but has much lower cost. With this new cathode materials, we are able a 25% cost reductions. So the last challenge I'm talking about, I like to talk is the battery safety. The safe operation of lithium battery really rely on a thin layer that is a solid electrolyte interface, SEI. As I show in the video, a good SEI should enable the lithium collation into the graphite without any lithium dendrite formation. Lithium dendrite is very dangerous, will cause the fire of batteries. So despite its importance, SEI is probably the less understood components in the lithium batteries because its nature is really beam sensitive. So here in my study, I select non-destructive tools, EQCM and AFM, to quantitatively monitor the SEI formations. By collecting this quantitative information, we can conclude SEI formation will separate into 4 stages instead of single stage as reported previously. So here we have this game figure to summarize our discovery. So we found first, in the first stage, the SEI will form the lithium fluoride. This is usually overlooked in the previous study. And the following, the major SEI components, LEC, will form in the second stage. And then the SEI will mature and grow thicker to block the further decomposition of electrolytes. In the last stage, the SEI will age with some new inorganic components forms. With these understandings, we have developed a new series of electrolytes that are non-flammable and can build better SEIs. So with these strategies, we could completely solve these safety concerns. In the last, I'd like to conclude my presentations. So we developed some multi-scale characterizations that reveal lattice string is the root cause of battery failure. Further, we invent a strain retardant approach that can unlock a higher energy density and extending the cycle life. To reduce the battery cost, we developed a new cathode, cobalt-free cathode materials. And in the last, we dig into the SCI formation mechanism and design some new electrolyte to promote battery safeties. With this strategy and continuous efforts, I'm very confident we will move to a future where the entire plate will be powered by lithium batteries. To end my presentations, I like to acknowledge our sponsor for the funding support, but also like to thank our group member and collaborators for the hard working. So with that, I like to thank the audience opinion, and then I'm happy to take any questions.
Thank you very much. Who would like to start? Lanfu?
Yes. Thank you very much for your nice presentation, and you present quite nice vision about all this in a particular study to address different problems, which are very important for the battery application. I just want to understand a little bit your vision, how to really take it up to the real application side. How that what's your sort of plan or vision to moving forward?
Thank you so much. Actually, I do not have enough time to explain more technology, but I like to say there are several technologies have been commercialized, like the cobalt-free cathode materials, because the industry really care about the cost. So the NMX is definitely commercialized already, and then other technology like the electrolyte, I mentioned that is not flammable. That electrolyte has also been licensed to the industry partner, and now is using the electrobus already.
Excellent, thank you. So what is your next plan then when you've already licensing your technology? So what is the next big step then?
Well, yeah, it's a very good question. So honestly, I'm still working on to find some strategy to solve all these problems. But I realized that is very, very challenging. So my understanding is this: instead of finding one strategy to solve all these problems, we probably will go with another directions. We will develop some battery with different functions. For example, we can develop a battery have the fast charging functionality, or that can use in the electric vehicles, right? Or we can develop some the battery for a long cycle life that can use for energy storage. So in the future studies, I will contribute to find the new strategies to solve each problem, and also we never give up to find the single strategy to solve all these problems.
Okay, thank you.
Yurai? I saw your finger going on first.
Yeah, beautiful work. I love the movie from the Nature paper. I'm wondering to what extent the approach you developed is applicable to other materials, because lithium-ion battery are important and conventional materials will continue to be used there, but can you basically generalize it more? Like a sodium-ion battery, pick the momentum, but different anodes, for example, are used, and so on. Yeah.
Definitely. Honestly, we are working on lithium-ion battery and beyond lithium-ion batteries. Sodium-ion battery definitely is another very promising cathode materials, because sodium is even cost efficient than lithium. So definitely we are working on sodium-ion batteries. So we have several works published in the high impact journal about sodium, but I do not have time to expand all these topics. Yeah, the answer is yes, we are working on multi-scale and also the different area like a sodium battery, lithium oxygen battery as well.
Well, thank you. If there are no more questions, then in the sake of time, let's move on to our next candidate, GITAKA Jesse. Yeah, you're welcome. From the University of Nairobi. who will be talking about development of point of care and game diagnostics for Africa.
Yeah, thank you very much. I am now sharing my slides. Can you see them? Is that okay?
Yes, I can see them.
Just put them into the presentation mode.
Super nice. That's okay. Yeah. It's good.
Perfect.
Floor is yours.
Good. Thank you. Thank you very much. I'm really happy to be here to present my work. I'm Jesse GITAKA from Kenya University, and I'll be presenting on iFast for point-of-care diagnostics in low-resource settings. So basically, my background, I'm a physician scientist, and we have the motivation to leverage on technologies for pathogen analysis, and our chosen technologies, which I'll be talking to you about today, is on the iFast and ATP readout, as well as combining iFast and LAMP amplification as strategies. So just to give you a quick background on use of magnetism in microfluidics, we know that magnetism offers relatively high forces at the piconewton range. Permanent magnets are cheap and also very powerful, and the setup can be as simple as placing a magnet on a chip, or can prepare more complex setups for refined control. And fortunately, magnetic particles are commercially available, so we really do not need to make them de novo in the lab, and they can allow for a range of applications, especially, for example, when combined or conjugated to antibodies. And microfluidic processes, including trapping, focusing, continuous flow procedures, or droplet manipulation, can be achieved using magnetic forces. So in my group, we are using this immiscible filtration assisted by surface tension, in short, iFast. And here we combine immiscible phases or immiscible fluids in different chambers. So in the case I'm showing here, we have 3 chambers where we have an aqueous, oil-based, and then aqueous. And in the first chamber here, we can put the sample with paramagnetic particles, and then the interface between the aqueous and the oil-based interface provides a virtual wall through which magnetic particles which have been added to samples at this point can be pulled through into the elution buffer here using a magnet as shown here. And this way, we are able to isolate and purify analytes prior to detection process, enabling simple single-step washing in a fast manner, so basically seconds to minutes, and we can work with small volumes, basically microliters. And this super short video just indicates what I'm saying. So you can see that the operator here is moving the functionalist paramagnetic beads through the different gates or through the different aqueous solutions, aqueous and then oil-based and aqueous, using a magnet, just below the device. So we've also combined the iFast and the magnetism to the ATP luminescence assay for detection. So basically here using luciferase, and in the presence of ATP and oxygen, and using the recombinant firefly luciferase, you end up with metabolites, of which the light is really a major byproduct, and then we can use the light to indicate presence of the ATP generating cells, including bacteria. This strategy is highly sensitive but non-specific, because any cell producing ATP will of course be detected. So we have leveraged on these 3 strategies for detection of maternal infections. The major maternal infections that we focus on, including ureaplasma, mycoplasma, chlamydia, group B streptococcus, Gardnerella, and Neisseria, are a real problem, especially so in the developing world. These cause sepsis, stillbirths, premature deliveries, newborn deaths, and they require fast and accurate diagnosis to enable prompt treatment. Importantly, Group B is really a major or the leading cause of severe neonatal infections. However, mothers usually will not have symptoms to this infection. So basically, there will be no prompt for treatment when they attend the clinic. So for us to detect it, we really have to test for it to confirm colonization and then treat them so that during the birth, when the babies are born, they do not end up with this infection. The current methods include cell culture and microscopy. As you can see, cell culture may take too long, up to 48 hours to get results. It's expensive because you need equipment and trained personnel to do this. Microscopy, same, you need electricity, you need a microscope and trained personnel to be able to do microscopy as well. So we thought of leveraging on the iFast technology to be able to bring the different strategies together and then be able to detect group B streptococcus at the point of care. So here we, of course, in the first image here, using the immunomagnetic capture. So where we use anti-GBS functionalist magnetic beads to bind onto antigen on the surface of the group B streptococcus and subsequently be moved through using this magnetic force or through a magnet to the last chamber here, from where now we can do the ATP assay and then be able to quantify or detect the infection. So using this, we were able to isolate 90% of group B streptococcus within 15 minutes. Any more time that we added onto this did not seem to improve the capture efficiency. So when we combined the iFast and the ATP assay, we were able to achieve a detection of 250 colony-forming units of group B streptococcus per mil sample in 20 minutes total, enabling point-of-care testing for timely treatment. I shall now proceed quickly to talk of how we've leveraged on the iFast technology for COVID-19 diagnostics. So we all know that when the COVID pandemic started, there was a big challenge with diagnostics. There was a huge deficit of diagnostics all over the world. And you can imagine this was more so in the low, middle, and income countries. So with the WHO-driven mantra of test, 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 it was really important for us to find a strategy. We know that the gold standard is the RT-qPCR, which is very sensitive and specific, with a limit of detection of approximately 1,000 copies per mil. However, it is expensive, requires specialist instruments and trained personnel to operate and interpret results. And the turnaround time can be, even more than 1 to 2 days, since some of the places, because of access issues, it may take long. And in most of the low resource settings, this equipment was not available. So there was need to identify other options that really met the WHO assured criteria, which is basically affordable, sensitive, specific, user-friendly, rapid and robust, equipment-free, and deliverable to end users. The antigen lateral flow assays are great. They're cheap, easy to use, have a 30 minutes turnaround time, but they suffer the problem of sensitivity in most of the cases. So they have a high limit of detection, and they also depend more so on the swabbing technique of the operator. The Abbott ID Now and SafeAid Expert are also very reliable, sensitive, and specific, with less than 1 hour turnaround time, but they require expensive instrumentation that may not be available in the settings we're talking about. So we sort of now thought about seeing that our device is able to combine RNA capture, RNA separation, and detection. How can we come up with a device that is just that one device allows for all the essential steps? It can be used by a minimally trained operator, requires no specialized instrumentation, and you can achieve less than 1 hour or less turnaround time. And we thought the iFast device does this perfectly. So we of course had to first of all compare with the gold standard tube assays. So the tube-based lamp assay is really very well established, and so we wanted to see, can we be able to achieve the same when we put this on the chip on the device? And indeed, yes, as you can see from the gel images here, the tube-based, the on-chip and the tube-based really compared very well, and for both ORF1A primers as well as the gene-N primers. And we were able to detect 470 genome copies after 30 minutes of amplification, indicating the potential of use of this strategy. So, of course, for infectious diseases, you really want to just detect what you're looking for. You do not want to detect other pathogens. So for specificity, we used SARS-CoV-2 primers in the presence of HCoV OC43 and H1N1. And as you can see in these images for both ORF1A and GeneN primers, we did not have cross-reactivity between these different pathogen genomes. So we then were able to combine both on-chip extraction, so which just means we get a sample, put it on the first sample chamber here, and then do RNA separation. Okay, so using MagnaCell, which captures the nucleic acids, and then moving them through the different interfaces, aqueous, oil-based aqueous, and so on to the number 8 chamber here, where you can then put our lamp mix at 65 degrees Celsius here, and then be able to visualize. And using this, we achieved amplification at these conditions of 10 minutes extraction, 65 degrees Celsius RT lamp with GeneN primers, and 40 minutes amplification. And you can see for both of these experiments, the positive samples really turned positive, and the products were even visualized on the gel. And so indicating that indeed we could use this chip or this device for detection of SARS-CoV-2. So the advantage of the chip I've just described is that you can use it to you can use your eye to see out the color change from pink to yellow. However, there's always a push to have a more objective readout, such as a lateral flow. So other groups had developed the CRISPR-Cas for COVID-19 diagnostic strategy, which was really robust and versatile method, but you needed to have separate ports to be able to operate it, and that transferring from one port to another would introduce contamination. So we thought we could leverage on it to enable lateral flow readout rather than just the eye. So we could use a readout that is more objective, and anybody can be able to read it. So the hybridization of guide RNA and the targeted DNA leads to collateral cleavage of nearby non-targeted DNA. So using this knowledge, we can modify the single-stranded DNA reporters for easy readout using the lateral flow strips. So this just as shown here on this image here. And this can be improved for point-of-care use with streamlined sample preparation and fully integrated platform as the iFast. So here we had to re-engineer our iFast device and add more wells along this separation pathway, as you can see here. So we achieve RNA extraction on the first sample chamber, and then isothermal amplification on this chamber here, mark number 2, and then perform CRISPR-Cas12 detection with lateral flow readout in the last well here. This illustrates the real the chip in real life. So when we combined all the steps, we were able to verify and to indeed show that we could achieve the successful amplification and detection and visualization using lateral flow. For the free RNA, we were able to detect 470 genome copies per mil. But when we used viral particles containing SARS-CoV-2 genome, we were able to detect 1,000 copies per mil in 1 hour with the conditions of 15 minutes of extraction, 35 minutes RT lamp, and 10 minutes CRISPR-Cas detection incubation. There was need to do multiplexing because for robust detection of the SARS-CoV-2, players, or rather scientists agreed that we need to detect at least more than one gene. So here we devised a new device so that we could have 3 lanes here, so that we could have a negative sample or negative control, and then have an N gene detection and an E gene detection as well. And as you can see on this image here, at the last chamber, you could then end up with doing a lateral flow test in the form of a dipstick. So using this multiplexing strategy, we were able to show that successful simultaneous detection of N and E genes of genomic SARS-CoV-2 RNA, approximately 1,300 copies per mil from one sample. Indeed, this is a huge advantage because you can then, be able to give a strong result for this pathogen. But remember, we are talking about low resource settings. So in low resource settings, you really do not want to have a situation where you need cold chain or so for reagent stability. So having reagents to be lyophilized is always a great advantage. So we lyophilized all the enzymes in their different chambers and buffers and the other reagents such as salts and like guanidine hydrochloride, and we saw that during the operation you just add some buffer distilled water to activate them and achieve the necessary processes in all the chambers as previously discussed. And this way we successfully performed on-chip integrated steps using lyophilized reagents stored for 7 days. In summary, we have shown that the iFast for SARS-CoV-2 is able to achieve a limit of detection of 1,000 viral copies per mil, which is very competitive when you consider when you compare with the other diagnostic strategies. And we've achieved all essential steps in one device. We have the generated proof of concept of where we are using simple heating source and manual pipetting, which are really things that not so well trained or highly trained people can perform. We have been able to detect N and E gene from one sample using multiplexing device in 1 hour, and we've shown the possibility of restoring reagents by lyophilizing, which really adds to the advantage of field deployability of this diagnostic. In the future, we propose to perform device validation with clinical samples and then proceed to clinical trialing of this device so that we can be able to use it as a public health control measure and a control tool. And the other advantage of this platform is that it can be used for other infectious diseases such as monkeypox and malaria. I really want to thank you all for listening, and I acknowledge my group members and collaborators for the excellent work they've been doing. Thank you very much.
No, thank you for an interesting talk. Let me start this time. I completely understand and dare with you that it's very important to have such devices that can work that don't need any resources. How well are your devices? How well can it be stored? Normally, often these kind of tests need quite strict storage requirements, especially cooling. They need to be refrigerated. How is that in the case of your samples? Because I can imagine in a lot of settings, you don't have the luxury to cool your samples.
Yeah, exactly. So in the initial optimization reactions, or experiments, we were using the reagents that needed cold chain. But as you can see towards the end of my presentation, I talked about lyophilizing. So this lyophilizing really enables you to keep reagents at the room temperature, and you really do not need super cold environments. So this is something that we've done, and the experiments are continuing for up to 6 months to see how the reagents inside the chips will perform even at that level.
That's very interesting.
Thank you.
Who else has a question?
I might just ask a very silly question, because with COVID, we know that the virus actually change. They change all the time, and have different strains. So how your method will really react to those kind of change?
Yeah, thank you. Super nice question. Yeah, so indeed COVID is a virus that keeps changing, and we've had several variants over the time. So for our assay, you only need to tweak the primers that you use for, so this called N and E gene, and you look at the reference variants or the new variants as they come, and then tweak the primers, and then when you use the different primers or the right primers for the right variant, you'll be able to detect it. So indeed, variant detection has to be performed using sequencing technology, and then once we know the variant sequences, we can then design primers which will then be applicable for using this diagnostic.
Okay, thank you. And I would also be interesting to understand that you mentioned also this technique can be transferred to malaria, which is a huge problem, yes, I know, in Africa. So, so fundamentally, is there some similarity in terms of the virus? So why you think it's easy to be transferable to that?
Yeah, exactly. So our technology is really looking for this. For the second part of my presentation, the technology is really looking at the nucleic acids. So as we all know, the different microorganisms of their different genomes and so on. So we are detecting the genes, specifically the genes. So we can be able to then just by tweaking the primers, we can be able to detect any other microorganism, which as long as we're able to extract the DNA or the RNA from the nucleus using in the first chamber here, then we can do the amplification in the in the RT lamp chamber and then be able to visualize it. So since we are looking at the genes, then this allows for really wide range of applications.
Thank you.
Okay, thank you. I think before we continue with the three last finalists for today, we will have a short 5-minute break again. See you in 5.
Thank you very much.
不再是奇迹，不再是幻想，此刻真感觉全世界对我鼓掌，不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。I can。没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can。 再是奇迹，不再是幻想，此刻真感觉全世界为我鼓掌，不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱，我装。
Okay, hello everybody. I hope you had a good short 5-minute break. I'm very happy to continue with our last finalists for today. And the first one out of this three will be Aristide GUMYUSENG from MIT, who will be talking about developing novel organic mixed conductors towards next generation iono-electronic devices. Please go ahead.
Thank you so much, Chris. And thank you so much, everybody. Good morning, good evening. Let me first take a moment to thank iCANX to give me this opportunity to be part of this great cohort of young scientists, and also to give me an opportunity to introduce some of the work that I am and will be doing in my group at MIT. And my group started only a few months ago at MIT, where we're interested in developing novel organic materials, especially for smart electronics. And we intend to do so by designing new building blocks and also conjugated polymers, understanding how they behave in the solid state, and then designing bio-inspired electronics with the ultimate goal being able to mimic a brain function, and that is organic neuromorphics. And also allow me to take a couple seconds just to thank the students in my lab. Now the group is actually growing very fast, but these are the true young scientists who are behind some of the work that I'll be sharing. And so I got interested in this work because there's a recent boom in electronics that are coming closer and closer in contact with our body. And I'm sure many of us on this call are actually wearing either a smart watch or some kind of gadget where we're trying to keep getting closer and closer to the machines. And but the real question mark is if we keep getting closer, for example, if I take an example of the proposed Neuralink device by Elon Musk, or let's say a smart contact lens, how can we keep getting closer and closer to our body when the body is so soft, but our electronics remain very rigid? And so I thought this was a great opportunity for material scientists to start thinking about what kind of material candidates we can think about. And in my case, organic materials were the to-go-to candidate. So in order to actually mimic what the body does by detecting a different kind of stimuli and from learning, from light, from smell, we need to find materials that can actually talk the same language that the biological circuits do. And that is in neurons and synapses, actually signals are transmitted either chemically or electrically as form of ions. And so we need actually material that can do this, where silicon-based technology does not do a really good job of this. So that's where we started thinking about organic materials as ways to actually detect ionic movement and then translate that into an electrical signal that we can detect. And then from there, we can start designing these kind of sense, learn, and react kind of platforms if we can mimic the way biology communicates. And for this, let me share this very busy figure on purpose because this illustrates how actually versatile organic materials can be, and which is why we're interested in them. Organic materials actually from a molecular viewpoint and also a multi-responsiveness viewpoint, they have different properties that can be tuned either by triggering the environment or changing their property. And so this highly interconnected and highly multifunctional nature of organic conductors is what brought me into this field as a way to start meeting some of the needs that we need in terms of interfacing with biology. We can change both the color, we can change the volume, we can change the mechanical properties as well as electrical conductivity of organic materials using different inputs. And so we have in the literature, we have a few candidates, some of which you might have seen part of this series. We have the famous PDOT PSS, for example, the old P3HT, and a few other candidates that are starting to rise in the literature, which have demonstrated some promising performances when it comes to mimicking the way that synapses or synaptic transistors function. And this is due to the ability to actually uptake ionic species and change their conductivity. And this uptaking and release of ions is attractive in such materials. However, even though these materials are showing a great promise in terms of the device demonstration, we still have several challenges. For example, the famous PDOT PSS is actually very difficult to process for most people and we're still facing several stability challenges, making some of these candidates not feasible or not usable for real applications. Also, very strikingly to me, as a chemist working in this field, it's very striking that the field is only relying on a very few candidates, right? So there seems to be a materials bottleneck when it comes to advancing these kind of electronics for real world applications. And so for my lab, I decided to think about ways to actually use chemistry to design novel semiconductors. And in order to demonstrate a controllable or controlled mixed ionic electronic conduction, and also think from an application viewpoint, how we can design novel materials and novel new structures in order to demonstrate these smart electronics. And these smart electronics, as I mentioned at the beginning, we can think about biosensors or these electrochemical type of sensors. Here, I'll refer to them as organic electrochemical transistors or OECT, but also artificial synapses, which can be used for memory applications. And we believe that we can do this by designing materials that are able to uptake ionic species, here using either pendant site groups or other additives, and then using the conjugated backbone as a way to actually detect the structural changes that are caused by the ionic insertion. And so, my thought was here that since other fields such as organic solar cells or conventional transistor devices that benefited from the wide library of monomers that exist and the chemical toolkit that is available to us in order to design new materials. And so my question was, how come for these mixed ionic electronic conductors, we have not been able to benefit greatly from this chemical versatility? And I think the major challenge actually here is that in order to demonstrate mixed ionic electronic conduction, you're fighting between two different modes of operation. For ionic conduction, we actually want an open structure where we want more polar side chains, for example, that can allow for ions to go in. While for the electronic conduction, you actually want more compact, so highly crystalline structures where electrons can delocalize very easily. However, in order to find the balance between these two, I think we need to spend some time balancing these two antagonistic modes. But chemistry is very powerful, so we should be able to do this if we spend some time and design novel systems. And so this is what my lab is currently and will continue to work on in the future. So to illustrate how powerful this kind of a chemical tuning can be, let me use one example just for the sake of today. In this example, I'll take a very well-known conjugated polymer. Here I will refer to it as DPP. So this is this diketopolypyrrole DPP polymer, which is a very great electron conductor, right? So this polymer is known in transistor devices for its ability to conduct electrons along the backbone. So even though it can conduct electrons very well, we have to do some modifications to it in order to actually enable ionic conductivity along its backbone. So in this example that I will share today, we decided to start with this well-known electron conductor, and we started modifying it by making copolymers using functionalized arrow group here, conjugated comonomer. And we can use side chains that will allow for ions to be uptaken. And I'm more than happy to share more of the details on the structure later in our discussion. But for the sake of today, let me use it as a shortened version where I'll call it DPP NGT. Here at the end will stand for the amount of the polar side chains that we are appending on our backbone. And so my approach here was that this DPP polymer is actually not a highly crystalline polymer. It actually has an open morphology from the molecular dynamic simulation. As you can see, it's a semi-crystalline material. However, it's not a good ion conductor on its own because it's highly hydrophobic. And so my thought was, if we can figure out how to open its morphology, and we can actually increase its electrochemical activity. And so we do this by the copolymerization strategy that I mentioned, where we start adding more groups that have polar groups appended onto them. And from the molecular dynamic simulations results, actually, we see that by doing this, we're not perturbing its morphology that much. We still retain the semi-crystalline nature. And as you can see from the AFM morphologies, we actually have very smooth without any phase separation, even after this copolymerization. And the first question we wanted to ask ourselves is, how much are we sacrificing the electronic conductivity or electronic transport of this polymer if we want to use it in transistor devices, for instance? And so, and by that, I mean that if we increase in the percentage of the polar functionalized components of the backbone, are we sacrificing our charge carrier mobility capabilities in our devices? And so we started with transistor devices. This is a conventional FET device. And then we tested how much of the mobility or how much of the charge transporting capabilities are we sacrificing by making these copolymers. And as you can see here, the on-off ratio is actually not that greatly sacrificed. And here, the thinking is that we're adding polar groups. So these are oxygen-containing groups, which will be serving as charge trapping sites in FET devices. But as you can see, the on-off ratio is conserved. But as you look at the mobility, we are indeed sacrificing some of the mobility, but we have some control in terms of how fast the mobility can drop. But even if we have 50% of our backbone containing these polar groups, we're still remaining mobilities as high as 0.01 centimeters squared per volt second. So in this class of material, this is not poor conduction given how much polar groups we are adding. But then the key component that we're interested in is actually, can we use these materials now in these electrochemical or electrochemically gated transistor devices? And so here we tested these polymers in these OCT devices where we're using either an aqueous and non-aqueous electrolyte. For aqueous here, we're trying to mimic environmental, biological environment or physiological environments. And the first key property we need to look at, are we actually enhancing the electrochemical or redox activity of these polymers simply by making them into copolymers containing polar groups? And indeed, as you can see from the electrochemical behavior, electrochemical results, you can see that by increasing the amount of the polar groups that we have, we are indeed increasing both the capacity and the redox activity of our polymers. And here, as you can see from the spectroscopy measurements, we are also able to show that this is indeed a property that is happening in the bulk of our polymer. That is, the entire polymer film is actually able to uptake ionic species, and then we can detect that by its absorption spectra. And so this is exciting because now we have some kind of control in terms of how well we can uptake ions and modulate the behavior of the polymer. And this is important for the above discussed way of mimicking how synapses and neurons communicate in our body. And so now when we test the transistor devices in these devices, we can see that not only we are determining how well the device is able to uptake ions, but we can also show that we're also controlling the speed of these devices. And speed here, let me quickly comment that in biological systems, speed is important because different analytes, different metabolites are released or uptaken at different speeds. So here we have some control in terms of how well the device can retain ionic species, but also we were able to modulate the response of the device to the input voltage, where the input voltage here translates to the amount of ions that we inserted. But more interestingly, here I'm showing this figure on the right, which shows this mobility capacitance product, where actually it seems like we need to spend more time when it comes to optimizing how well a material can uptake ions at the same time conduct electrons. And here I started my talk talking about mixed ionic electronic conduction, and this is where we need to find the sweet spot. It seems that increasing the capacity of our polymers here by increasing the amount of the polar groups along the backbone is not always the key, because we're also sacrificing how well the polymer is able to conduct electrons. And so it seems that we need to find optimized conditions. In this case, the example of the DPP that I'm sharing, we can find a sweet spot somewhere around 20% of the backbone being functionalized with polar groups. And this is really exciting for us because we have both the controlled ionic uptake, but also controlled charge carrier mobility in our transistor devices. And why is this important? This is important because now we can actually start teaching our transistor devices. And here, once again, I opened my talk talking about how we need to mimic synaptic function or neuronal communication. And so now we can actually start speaking the same language as synapses or neurons. And because here, as you can see, if we take this lateral version of our device, we can use a gate contact as a way to actually write or send a command into the electrolyte, thus pushing some ions into our polymer channel, and we can read out the output current. And here you can see that our devices are actually able to respond to a series of very small pulses. And here we're using 40 millisecond volt pulses. And this is quite similar to the ranges that we find in biological tissues. And as you can see, our device is able to populate different memory levels in response to a series of these pulses. And also note that we're using very small amount of voltages, even though our devices are still on a millimeter scale. And so this, all the power consumption can also be scaled down if we make our devices smaller. And so this is important because, as I mentioned, we're now starting to speak the same language as the synapses or neurons communicate in our body. But also, most importantly, we can actually intentionally use these devices for this learning and forgetting properties that we find in the body. And what we do, how we do it here, we're applying a series of pulses in one direction, and we can erase that memory by applying opposite polarity of the gate voltage. And so this is really important because we have control in terms of how well ions can intercalate into our polymer film. We can then modulate the capacity of our channel material, and then we can demonstrate this reliable insertion and extraction of ionic species, which is the same way that our neurons and synapses communicate. So why is this important to us to design new materials? Because now simply by copolymerization strategy, we have actually started opening up novel opportunities in terms of materials. For those of you who know me a little bit, you know that I like to mix things, and here I'm using one example to demonstrate what I mean by that, where actually with this copolymerization strategy, we've been able to show that we can start to modulate its nanostructure simply by making composites. And here, if we take our DPP copolymer that I mentioned, we can mix it with the soft matrix, and we can actually show that we see that we can control the nanostructure, the physical property of this material. Why this is important, at least for us, we think that this can help us improve a cell viability, also the mechanical deformability of our films, which will be important when it comes to being able to detect biological signals and do so for a long time at the interface of the body. And so here, the example of DPP that I showed, not only does it allow us to demonstrate electrochemical properties, but it also allows us to demonstrate new capabilities when it comes to tuning the physical properties of devices, which we're currently investigating in terms of demonstrating on-body function of these devices. And so with my group, we're definitely excited about the potential in polymer design, electrolyte development, and also novel organic circuits and bioelectronics, simply by designing novel organic conductors as opposed to relying on only commercially available or very few candidates that have been reported. And our strategy actually has also opened up more fundamental investigation in terms of mixed ionic electronic conduction. And this is the field that I think a few of my colleagues already talked about its relevance in terms of energy storage, electrocatalysis, but also sensing. And so simply by spending some time understanding how we can couple this ionic electronic conduction would have an impact on a variety of fields. And also not to forget the socioeconomic impact that we believe that these electronics will have in terms of restoring function, especially motor function, touch, vision, and all others by mimicking the way that biological functions are operated. And so with that, I'm really happy that iCANX allowed me to give you a flavor of what my group will be working on. And we're really excited about the opportunities that we're opening up simply by designing novel organic conductors. With that, let me thank again my group and thank some of the collaborators that have helped us with some of the discussions. And let me take a few questions from the committee for the discussion for today. Once again, thank you so much, and I appreciate the time and your attention.
Yeah, thank you very much. Who would like to start?
Maybe I can
Nicholas?
start.
Nicholas was just a microsecond faster.
Aristide, wonderful work, really very exciting and very new and innovative. Just a minor point, I noticed towards the end you were talking about copolymerization for the composites, bringing them together, but you used the word mix, and that got me worried because mix is not copolymerization. You're going to have delamination, you're going to lose some of the properties. Did you mean really some kind of a reaction even in that case?
No, actually, I should have clarified that. In this case, actually, I should have said blending. Where so we take our semiconducting copolymer and then we kind of suspending it into a matrix. So mixing, yeah, you're right. I should be some points should be taken off for that. So thank you for clarifying that.
Okay, thank you.
Yeah.
By the way, nice Greek name, Aristide.
I have no idea how my parents came up with that from Rwanda.
Okay, Yuri.
Aristide, I have a bit more general question.
Yeah.
I'm just wondering whether you see yourself more as a direction for yourself, as more like a designing, conducting polymers, or moving towards ionotronics and devices.
Cool. Actually, that was one of the questions I definitely had to answer when I got this job 10 months ago, where I think that developing new materials is definitely important. And my background is actually in chemistry. At Purdue, I did chemistry as a grad student. So I think designing new polymers and actually having a synthetic component to my research will be important. But we would like to also have the expertise on making these electronics ourselves so that we can kind of bridge that gap between the material makers and the device engineers. And so in my case, I would like to stick to the chemistry because that's where I feel comfortable, and then inform the device makers. And so being able to be at the interface between those two fields. Thank you, Yuri.
And about blending, do you think that inorganic materials added to the system may help with the transport properties, both electronic and ionic?
Yeah, I think yeah. So that's a very, very good point. So I know in your case you're interested in vaccines. I think actually finding some kind of way to hybridize between polymers and let's say vaccines or other porous materials. This could actually solve some of the key issues. Where, for example, if we can use some good conducting polymers as spacers in vaccines, I'm not sure if that's maybe a premature thought, but I think yeah, we can find a way to hybridize between organic and inorganic in order to bring the good ionic conductivity and also bridge the gaps between highly crystalline and amorphous domains. That would be a really great strategy. And I'll probably be reaching out to some of your students or even some of your collaborators to see what we can do in that regard.
Sounds good to me.
Maybe one very short question for me, and please a very short answer. Then we can so we have time enough to move on to the next candidate. I see your device a little bit like electrochemical cells, and other groups have also worked with PESS and did the same type of measurements you just showed.
Yeah.
Why are your materials better than those?
Yeah, I think great point. So PESS has been around. It's a great conductor, and it's definitely been used for a variety of properties or applications. But I think we should definitely give credit to the material, but I also think that we should not be overwhelming the material. It cannot be used for everything, right? PESS is a great conductor, but when it comes to modulating its conductivity, its conduction state at a low power and a very low energy penalty, I think we can do better in that regard. So I think PESS has its role, but when it comes to achieving other properties, let's say optical, mechanical, we can design other material to complement PESS.
Yeah, maybe I should have been a bit more specific. Those works that were blending or adding small molecules to PESS to tune its properties. You blend different big polymeric molecules. So why is big polymers better than small molecules?
Yeah, so I think for example, in the case of PESS, actually the commercially available one, usually there's also lack of control in terms of the length of the conductive chain. But so you don't really have much of control in the morphology that you can get. So this is just one example that my student just looked at. But we have tunability in terms of we can control how well connected these nanostructures are. We can, by the way, these things are stable up to 300 degrees C, which is something that PESS cannot do. And so we definitely have more room when it comes to designing new backbones and then generating new nanostructures.
Okay, thank you. Very clear answer. Thanks. So let's move on to our next finalist for today. Changyong from Case Western Reserve University. And the talk will be about self-powered stretchable electronic systems. Yeah, I cannot hear you.
Can you hear me now?
Yes, now I can hear you.
Okay.
Okay, the floor is yours. Go ahead.
Okay. Good evening. Good morning, everyone. So I'm T. Stoll from Case Western Reserve University. Thanks, Alice and the committee for giving me this opportunity to present our work on the stretchable electronic systems from the low-dimensional nanomaterials. So my research group aims to understand the fundamental mechanics and physics of advanced materials and to design and manufacture the novel electronics and the machines using advanced technologies. I expect to address the grand challenges in healthcare manufacturing, environment, aerospace exploration, and some other fields. So my group currently is focusing on three major topics. The first one is soft materials and manufactured materials. The second is self-powered soft electronic systems. This including some transistors, the sensors, energy harvesting, and storage devices. The third one is the soft robotics and soft machines. So today I will show some work on the self-powered soft electronic systems. The keyword is soft, and we work on some soft themes using combined method of theoretical analysis, numerical method, simulation, and experimental study. The first part I would like to discuss the printed flexible stretchable electronics. So the printed self-powered stretchable electronics together with the machine learning and the data science can be used for a variety of applications from the smart agriculture, smart cities, smart vehicles, and smart manufacturing and the industry 4.0. So in particular for the smart healthcare and the precision healthcare, we need some stretchable designs. So in the past decades, we have observed dramatic advances of the emerging soft electronics for many applications. Some examples include the sweat sensors, epidermal sensors, the food sensors, and the human-machine interfaces. So this device has a huge market. Actually, it is estimated that the wearable electronics market will grow to about $50 billion by 2026. So the key features of these emerging electronics is to maintain their stable performance and functionality when subjected to large strains, such as the bending, the stretching, and twisting. So this requirement poses the new challenge for the materials, structures, and manufacturing processes. Based on the potential applications, it's a very broad application. We need to reduce the fabrication cost and increase the product through output. So printing method has been a major driving force in this field to achieve the goals for large scale, large area applications. Currently, people are mainly using the four different methods to fabricate this. The screen printing method, the ground veneer printing method. Okay, the inkjet printing method and the aerosol jet printing method. So each of those some pros and cons. But my group has some unique activities in fabricating devices using the screen printing and the aerosol jet printing. Aerosol jet printing is a relatively new technology. It has automation methods, either using the ultrasonic and the pneumatic automation. The viscosity of the printing inks can be as large as 1,000 centipoise. So we can use it to print the conducting materials, semiconducting materials, and the dielectric materials using one single tool. And for different kind of electronics, even we can use it to print the bio inks to develop some biomedical devices and assays. So my group has used it to fabricate different kinds of the transistors, memory resistors, and supercapacitors, as well as the three-dimensional structure of the electronics. We worked on a few aspects of this technology, from the ink development to the device integration.
So for the first time, we fabricated the fully printed carbon nanotube thin film transistors using one single tool and process. We also investigated the effect of the different configurations for the transistors' performance. So we successfully reduced the hysteresis of this carbon nanotube thin film transistor to the acceptable level for the real applications. So here for the top gate design, we achieved a very small hysteresis of 0.2 volt. So we also examined the stability of the printing dielectrics. So using the stress analysis, so from the increased the bias voltage from 0 to 40 volts, we didn't see any significant change of the transfer curves. So our fully printed flexible CNT TFTs has excellent performance. It's in both bending and reliability tests. So the device can still works very well, even bending for over 1,000 times and a small radius, 1 millimeter. So the compared to other dielectrics through in literature, so our printed dielectrics give a very attractive performance with a small hysteresis and the small threshold voltage. So for a 2 months period, we observed the hysteresis, the threshold voltage, and the mobility of the device actually can keep in the same level. That means the printed device can be used for long term without any encapsulation. To fabricate the flexible and stretchable electronics, we usually need a suitable substrate. Different kinds of materials, including the polymers, silicon rubbers, hard layers, and cellulose fibers, people use for the substrate materials. However, these materials are not comfortable to wear in a direct contact with human skin. So the textile as one of the most available cloth materials is an ideal substrate for flexible, stretchable wearable devices. Due to its outstanding mechanical properties, it's a good flexibility and softness, is conform contact with the skin, and it has a very excellent wearing comfort. So it's desirable to develop a new smart the textiles, that can integrate both the functionality of electronics and the comfort of the textiles. We developed a screen printing process to deposit a water-based conductive ink on the textile surface with the pre-painted mask. So after we printed, we also need invisible layer, waterproofing agent on top of it to protect the cracking. The water-based conductive ink was made of silver fractal dendrite and a transparent binder, and with a mixture of solvent with the divisor EG and the EA. So here we dispersed the conductive silver ink has a hierarchical structure, so it can form a percolation network after printing. So with the same conductive failure percentage, we adjusted the binder ratio, and we can get different inks, and we find that the 45 and 55, it can stay for a long time and to be used for the quality printing work. We found also the conductive ink has a low heat resistance, so we selected this ink 45. We use this ink, we can print it high resolution, nice the circuitry, and on the top surface and the cross section SEM image, we can see the percolation network formed by the silver fractal dendrite. These are 4 different inks, and for the ink 45, we stretch the substrate to 100% strength. We still maintain a good intact state. Actually, for the deformation mainly comes from the gap regions on the surface, and you can see it forms some wrinkles here. These printed textiles have excellent water resistance, and it also has a good air permeability and water resistance. So even immersed in the water for over 24 hours, it still works quite good. And after for multiple washing around, it still works quite good. With the excellent electrical performance of the e-textile, we can use it to develop, fabricate the aesthetic smart clothing, so that we we can build the dual heater using the e-textile embedded in the clothes and help to manage the body temperature. The string sensors can form the to use for monitoring the motion states of the user, and its performance will not affected by the sweat and water. So inspired by human skin, we recently proposed a new textile-based self-powered tactile sensors for multiple functional sensing. So this tactile sensor consists of two major parts to mimic the human skin: the triple electric generator layer for mimicking the fast adapting mechanical receptor, and a piezoreceptive layer for mimicking the slow adapting mechanical receptor. So it can be used to detect the pulse rate and the human motions, voice patterns, and recognize the materials types. So this is the prototypes of the sensors. So this SA sensor actually can have very good have very fast response and recovery behaviors, and the repeatability is quite good. The SA sensor can be used to monitor the physiological signals and human emotions. And for example, here it can detect the pulse rate and distinctly different the patterns of the PTD peaks. So the FA sensor with the finger print-like patterns can detect the surface textures and identify the material types. So if combined with the machine learning algorithm, it can distinguish the materials with an accuracy over 99%. In addition, the new skin-inspired sensor can resolve the complex stimulus controls, and it can be used for the robotics control and to detect the signals and do some artificial skin applications. In the second part, I'm going to discuss, the stretchable energy devices and to build the compatible stretchable electronic systems. Maxine is one of the most promising materials for wearable devices. It has some, the high conductivity, high capacitance. It's also solution processable. However, we found that there are little work on the stretchable devices using Maxine at that moment. So we find actually the major challenge is the cracking issues of the Maxine. If applied 100 or even 15% of the strain after releasing, it generates a loss of the cracks. So this affects its conductivity significantly. Inspired by the reinforced marks in civil engineering, so here we added some reinforcement Maxine with reduced graphene oxide. And after adding a small percentage of the reduced graphene oxide, we can completely remove the cracks and to maintain a good the standards of the electrodes. So the cracks generated in the relaxation process are attributed to the high mechanical modulus and the small flakes size of the Maxine film. Compared to the Maxine, the reduced graphene oxide, it has large flake areas, and the lower ion modulus. It also has a high surface energy, so it can increase the face-to-face interactions. The double layer supercapacitors made by the Maxine reduce the graphene oxide composite can have very good stretchability, reliability, and the excellent electrochemical performance. The applied strings actually had little influence on the electrochemical performance of the device. Carbon nanotube forest is another promising materials, for developing the sensors, supercapacitors. But the people before mainly using the line down the carbon nanotube films. So we using the carbon nanotube forest, to build even more promising materials. Here, the devices. Here we propose the new design and manufacturing method to fabricate the stretchable supercapacitor and the tubes. So using the crumpled CNT forest. The CNT forest here we're using thermal oxidation CC CNT forest to the stretchable substrate. And the crumpled CNT forest-based stretchable device, demonstrate the excellent the electrochemical, the CV curves and the charge discharge curves are not affected much by the applied strains. Even the applied strains larger than the pre-strains we used. This is for the biaxial case, and the biaxial stretchable device also have very good performance. And this here, this work actually is not only used for the carbon nanotube forest. It can be extended for other materials like the nanowires, nanorods, and nanotubes for stretchable devices. So this work was highlighted by the Nature Brief and reported by many other devices. In the future, my group will devote to innovate the superior solutions to grant challenges. These software solutions will contribute to various fields from the wearable device into human machine interfaces and the resilient society and smart societies. Especially for the personalized healthcare, I will leverage our design and fabrication activities to improve the device performance, the interface bounding issues, and enable the device to be able to learn self-care and to be more intelligent. So on the other hand, I will pay more attention to the scalable manufacturing with the soft electronics for real applications. Some key problems involve the mechanics of thin films, adhesion instability, cracking, and multiple physics field coupling effect. I hope to build the scale, the roll-to-roll fabrication platform for high throughput manufacturing with soft electronics. So finally, I summarize here and so we developed some, the printing, the stretchable electronics and the energy devices. Want to build some self-powered stretchable electronic systems. Finally, I want to acknowledge my group members and the collaborators. Thanks for their efforts and support. We also want to, I really appreciate the founding agency to support our work. Thank you very much.
Thank you. Who would like to start with asking questions?
I can do work in this field. Nice talk, Chase. I'm wondering, what do you see as the key problem in this very hot area of textile wearable electronics? Is this materials, it's manufacturing, is it device design, anything else?
Oh, Yuri, thanks for that question. That's actually, I think the challenge comes from a few aspects. One major problem is the interface issues, the interface bonding string, and also, these are porous structures. And when you printing, you also need to do some, the specific treatment and how to maintain is a good, a stable, reliable interface. For the another issue is, for the textile based, we needed to accommodate the washing and the durable issues, and how to make it more robust to survive not only the strings and also the water and humidity, the environment, and how to affect the environment. The water temperature change to affect the device performance. Development materials is also a significant the aspect to make the device much better.
I also saw that Nicolas has a question.
Thank you.
Chase, was a very nice talk. I'm a little bit perplexed because what you presented and what the field is turning to is development, processing, how not to have delamination, how to come up with faster methods for combining the various layers and so on. There is a very dear colleague in another university who publishes one paper a week. I'm not kidding you. One paper a week on new types of electronic systems and so on. Are there any fundamental problems that have not been solved yet? Or is the whole thing putting things together and coming up with something new,
Oh, Nick, thank you. That's a very good question. Actually, this is some, if we enable the device stretchable, we have two strategies. One is to develop some structural stretchability, based on the structural designs, like the work we did and George Ryder's group, they did some work. And another is eccentric, stretchable materials and to make it stretchable. For both these has some some pros and cons, and here it's not a simple work. We just laminate them together and then form the structures. Here, for example, for the film, if it's a uniform film, it's has some standard the procedures. It's make the fabrication process easier. But it's different. For example, here we use the carbon nanotube forest. It's a different story. And how we can make them to more robust, and if we design device, how to make it more accurate, that's something unsolved. Here, for the instability, for example, we have anisotropic layers on top of that. And if we have multiple layers, it will form a more complex structure, how they will deform and evolve. And if you change and how the deformation will affect the sensitivity and the detection range, we don't know yet. Even for the carbon nanotube forest, we have no mechanics models to guide the designs to do that. Because currently we're using the isotropic materials.
I think you answered it. I think, yeah.
Okay.
I work with Nanshulu. I have heard all these things all the time. And you did mention my dear friend John Rogers. I don't know how they do one paper a week, but they do. Anyway, thank you very much.
Yeah.
Thank you.
No, thank you. And I think for the sake of time, we have to thank Chase and move on to our final contestant for today, Nako Tsusuka from ETH, and she will be talking about nanoscale aptamer biosensors. The floor is all yours when you're ready.
Thank you so much for the introduction. Hi, everyone. I'd like to start by thanking iCANX and all the committee members. It's a real pleasure to be here. And I'm very excited to tell you a little bit about what we work on in terms of nanoscale aptamer-based biosensors to monitor brain chemistry. But to start out, I wanted to really tell you that the brain is extremely complex. I think everybody knows this, but we can really break down the way in which two brain cells communicate to two mechanisms. The first is an electrical action potential that triggers the release of these small molecules called neurotransmitters that then diffuse through the gap, bind to the next receptors of the next neuron, which then triggers the next action potential. So while simplified, it's really, what I want to emphasize here is that it's important to understand both mechanisms, not just the electrical, but also the chemical. And if we take a look at what's been done so far, there's been a lot of fantastic papers that have come out that do electrical recordings. You can see over a decade ago, they can use these flexible biocompatible electrodes that can be put in vivo in the brain. But when it comes to chemical measurements, this is a little more challenging. But in order to understand various diseases such as Alzheimer's, Parkinson's, and depression, it's really important that we have means to quantify the neurochemicals simultaneously to the electrical measurements. But the reason why chemical measurements is actually very challenging is you can imagine being in this complex environment trying to capture one small fish in a sea of similarly looking fish. And if we talk about this in terms of chemistry, it's like differentiating dopamine from norepinephrine, two extremely important neurotransmitters that only differ by a single hydroxyl group. And so the key challenge here is to be able to develop methods that have the adequate selectivity to be able to quantify the neurotransmitter of interest. But I wanted to first share the state of the art when it comes to neurochemical measurements. The first is fast scan cyclic voltammetry, where you can take a carbon fiber microelectrode and directly implant it inside the brain of a mouse. This method utilizes redox chemistry. And so at the surface of these microelectrodes, dopamine can be oxidized, where these hydroxyl groups become these ketone groups. And while this method is very powerful, one of the challenges I already mentioned is distinguishing dopamine and norepinephrine. But also the precursor to dopamine, L-DOPA, also has these structural similarities of the two hydroxyl groups. And therefore, fast scan cyclic voltammetry often has challenges when it comes to selectivity. An alternative method is microdialysis. In this case, you can take a localized sample from a brain region. This sample has to go through a semi-permeable membrane to collect the small molecule analytes. But then in order to do the analysis, it's actually quite challenging. You have to first purify through high-performance liquid chromatography, and then the sample has to be pre-treated prior to analysis by mass spectrometry. So for looking at very low concentrations of the analytes of interest, it's oftentimes not sensitive enough in order to detect the molecule. And so while these are powerful methods, there is room for improvement, and that's what I'll talk about next, where in order to tackle the selectivity, we work with DNA aptamers. These are single-stranded oligonucleotides that can undergo large conformational rearrangements upon capturing a target of interest. The selectivity from aptamers comes from the fact that in the presence of the wrong molecule, these aptamers do not undergo conformational dynamics. And a lot of my PhD work really focused on characterizing these structure switching by various methods in order to understand the magnitude and how the molecule interacts. Another reason why aptamers are selective is because they are selected artificially in vitro. And so very briefly, you start out with a DNA library of approximately 10 to the power of 14 strands. You incubate your target of interest, let's say dopamine, and then you see what sequences bind. Then you can get rid of any of the sequences that did not bind, but then this is the key step. You can also do counter selection, where you can then incubate very large concentrations of non-specific interference, such as the norepinephrine molecule I talked about before, and then you can amplify the sequences that are already selective. So you can differentiate the sequences at this point. In this selection procedure, then this process can be cycled with multiple rounds, altering the environment with higher stringency in order to identify good aptamers. But once we identify these aptamers, we also have to couple them to different platforms. And in our case, to have the nanoscale resolution and also adequate sensitivity, we work with nanopipettes. My PhD work worked with transistors, but this is a novel platform. And with these nanopipettes, these pore openings are approximately 10 nanometers in size. And so we really confine the molecular binding events in these nanoscale orifices. And while this is really powerful in terms of the confinement, the other advantage is that when you measure in complex environments, a lot of the non-specific molecules, such as larger proteins, can't enter the pore. And so we already have minimal biofouling thanks to really localizing the biosensing inside of these nanopores. And so when I first joined the ETH Zurich as a postdoc, my vision was to be able to start to do electrical and chemical sensing at the same time. Our group specializes at the Laboratory of Biosensors and Bioelectronics in patterning neurons in vitro and very precise architectures on the surface of microelectrode arrays. And so our group specializes in the electrical measurements, and what I wanted to bring to that was the chemical aspect. And so you can imagine that the synapses are at nanoscale. They are approximately 20 to 50 nanometers in size. And the long-term vision is to really start to get close to these interaction points with nanoscale sensors. But I'll tell you that along the way, we also found other applications that we can also use these nanosensors for. So I want to walk you through how these sensors work, and that we have two quasi-reference silver-silver chloride reference electrodes, one inside the pipette and one in the bulk solution. What we physically measure is the current that goes through this nanopore. If we modify the inside of this nanopore chemically with these DNA aptamers, what we get is this ion current rectification event. It's basically a non-linear behavior in the current response when applying a linear voltage. This is due to the conical geometry of the nanopipette, also the size of the orifice, and the surface charge density inside of this nanopore. And therefore, if we keep all the dimensions the same, but the aptamer undergoes this conformational change where the negatively charged backbone is rearranged in this confined area, now we see changes in the charge density, and we can really transduce this as a change in the current that is going through this nanopore. What's also nice about this method is that we can really track this difference in the surface charge density at different states of the surface chemistry. So we first start with the bare quartz pipette that is slightly negatively charged due to the hydroxyl group, and you can see that it's slightly nonlinear in the behavior. Then we assemble aminosilanes through vapor phase chemistry in order to create a monolayer. And finally, we functionalize the DNA aptamers that are highly negatively charged. And so from looking at these curves, maybe it's difficult to understand the differences in the surface charge density, but we can quantify this through a value called the rectification coefficient. This is the ratio, the natural log of the ratio between a current at a certain positive voltage and the same magnitude at the negative voltage. And for the bare quartz, you can see that it's slightly negatively charged. For the aminosilanes, it's positively charged. And then finally, when you put the negatively charged DNA molecules, we see this higher rectification or higher negative charge. So we can really track the surface chemistry. We first developed serotonin-specific sensors, and you can see that from the baseline, which is just in pure neurobasal medium, and this is a media in which neurons are cultured, so it's a complex environment, there's an increase in the current with increasing amounts of serotonin. Looking at this on a calibration curve, where these are error bars for 8 independent sensors, you can see that we have sensitivity in the picomolar nanomolar range. And one more thing I want to point out is the capacity to design really good control sensors. Because we're working with these artificial DNA molecules, we can retain the same number of bases, but then we can scramble the order to alter the molecular recognition properties. And so we always have a scrambled control that does not react to the molecule of interest. We also show that these sensors are selective. We can differentiate structurally similar serotonin analogs using these sensors. And so now we can really generalize these chemistries to other molecules, and we are developing novel sensors for various different neural metabolites. But because I don't have too much time today, I wanted to also show the adaptability for different applications in neuroscience. And for example, we can really directly quantify neurochemicals that are released in clinical samples. But because these are nanopipettes, they are capillaries that can be really integrated into patch clamp methodologies, we can also do ex vivo measurements in embryonic samples, for example, that are cultured on the surface of electronic microelectrode arrays and do sensor versus control measurements in localized regions. Further, we are implanting these sensors ex vivo in brain slices to measure endogenous release of different neurochemicals in different regions. While I don't have time to talk about these two applications today, I'm happy to take questions later. But I wanted to focus a little bit on the clinical samples since we've published on this work recently. When we talk about serotonin release, it's actually quite challenging because serotonergic neurons reside in the deep brainstem, which is highly inaccessible. And less than 1% of neurons in your brain actually release serotonin. And so we had a really wonderful collaboration with the Salk Institute, with the laboratory of Professor Fred Gage and his postdoc Krishna Vadodara, were able to differentiate human skin cells into induced pluripotent stem cells, which then take on this serotonergic neuron form. And so what's really powerful about their method is they can take patient-derived skin cells and turn them into neurons. But the reason why this collaboration was so fruitful is that they previously used ELISA, which is a really standard method for quantification, which uses a sandwich assay to quantify serotonin. And this method was inadequate in terms of sensitivity. So what we were able to do is to receive samples from them collected from serotonergic neural medium in which serotonergic neurons were grown, or a control medium in which these iPSC-derived astrocytes that do not release serotonin were grown. And in this very simplified diagram of the serotonergic system, you can see that serotonin is released from one neuron. They either bind to the next neuron or get reuptaken by a transporter protein. We can start to modulate this, for example, by adding high salt, potassium chloride. This induces neuron depolarization, meaning that the neuron dumps out all of its reserves of serotonin, and therefore you expect higher concentrations of serotonin in the extracellular fluid. Our sensors were able to quantify these differences that were conducted in a double-blind experiment, where we have the non-serotonergic cells, the astrocytes, do not show any response to serotonin. The serotonergic neuron medium showed 1 nanomolar concentration, which was increased threefold upon inducing the depolarization effect. And similarly, we modulated the system with an antidepressant. This is a commonly found antidepressant, citalopram, which binds to the serotonin transporter protein to block the serotonin reuptake. So now you also increase the amount of serotonin that is in your extracellular space. That's something that we were also able to quantify, where the serotonergic neuron amount was then doubled from 1 to 2 nanomolar. And what was also very interesting for the neuroscientists was showing that the acute treatment with citalopram, which is the 2-hour short-term treatment, actually ends up with the same amount of serotonin released for the 24-hour treatment. So we are really able to show these differences by directly quantifying in these complex medium samples without doing any kind of sample pretreatment. And so now that we've shown this with the serotonergic system, I mentioned before that we are developing new sensors for dopamine. And I wanted to finish up today by talking about a new clinical study that we are taking part in to show how these sensors can be used. For Parkinson's patients, the only drug that currently exists is this L-DOPA treatment, where they can take oral doses of this chemical that can then pass the blood-brain barrier and then be converted to dopamine, which is done through an enzymatic process. However, this enzymatic conversion of L-DOPA to dopamine is influenced by so many different things, such as the patient's BMI, what they ate that morning, whether they exercised or not. So it's very difficult for patients to know how much L-DOPA to take in order to minimize their symptoms. We have a lot of data in terms of brain fluid, how much dopamine is in the brain. And this is taken from a spinal tap, which is a very painful method. It would be so much easier to be able to quantify dopamine in blood or in serum. But the challenge is that they exist in very low concentrations in the femtomolar to picomolar regime. We have sensors for dopamine that can actually really adequately measure dopamine in these very low concentration regimes. And so we're now trying to upscale the production of our sensors and to multiplex so we can screen through thousands of clinical samples and to start making correlations between brain versus blood dopamine for Parkinson's patients. And so this is the outlook of what we are really trying to do in the next few years. And so with this, I'd like to acknowledge the group that I'm a part of at the ETH Zurich, the Laboratory of Biosensors and Bioelectronics, the wonderful collaborators I've had the chance to work with, the Apta Wine Club that consists of bachelor's and master's students, and I hired my first PhD student last year, so we're still a very small team, but I'm very excited about where our group is going. And with that, I'm very happy to take your questions, and thank you so much for your attention.
Yeah, thank you very much. Who would like to start asking questions? Nicholas?
Thank you very much, Dr. Nakatska. And I must admit, you're competing with the game of Croatia with Brazil. which for the time being is 0, 0. Wonderful work. I wish you good luck with trying to do passage through the blood-brain barrier. Many of us are trying to do the same thing, but I like very much how you combine the aptamers. And I don't have any comments or questions. I think this is wonderful work, and it is what you do now, and I wish you good luck, but it is a very, very important area. Thank you.
Thank you so much. I really appreciate your comments. Thank you.
I have a quick question. I'm just wondering about the use of quartz pipettes. They're conical, so they displace a significant amount of cellular material as you try to go into even a single cell. And of course, much more damage is done when you try to go deeper into brain tissue here. I'm wondering if your approach can be also applied to like a cylindrical nanotube-like structures that would allow you to probe deeper without doing much damage.
Thank you very much for your question. And so what we are currently trying to analyze is the extent of damage that we cause, because we now have 10 nanometer orifices compared to the traditional micrometer scale patch clamp pipettes. And so I think that the damage is significantly less, but of course, that's something we really have to analyze. And the deeper we go into the tissue, of course, because it's conical, we are going to cause more damage as it gets thicker. And so I only had the chance to talk about these nanoscale pipettes today, but we also do a lot of surface chemistry of aptamers on carbon nanotube-based transistor materials. We are really thinking about different platforms in which we can integrate these receptors and to use the conformational dynamics to transduce the signal. And so I think the nanopipettes really have their little niche in terms of doing these localized measurements. They're fast to make. We really make everything in-house within one day. And so it has their niche, but there's definitely ways to improve, for example, penetration intracellularly to create less biofouling as well as less damage to the tissue and the cell.
Also a quick question, just about your multiplexing, when you mentioned and to upscaling or to make things faster. Wonder, are you trying to do like the same function, just make them like more like integration, or you actually talking about the function? You are testing different concentration. What are you trying to do there?
So it's everything. And so we are expecting thousands of clinical samples from patients with Parkinson's. But then, of course, for quantification, we have to do standard addition measurements, which means we have to add known concentrations to those samples. And so for every sample, we are probably going to have to do 5 concentration measurements and also do, let's say, n=3 measurements with specific sensors and also controls. So it's just really upscaling from what we currently have. Luckily, I'm currently in an electrical engineering department at the ETH Zurich. And so we're really just looking to multiplex in terms of multi-channel amplifiers. So we can do 16 nanopipettes simultaneously rather than one measurement, but also maybe integrating some automation. So really just having 16 pipettes measure in one fluid and then moving to the next fluid. And so hopefully within a day, we can measure hundreds of samples rather than currently with a team of my students and I, we can measure tens of samples maximum.
So the key limitation or saying like the challenge is more about electronics, is it?
Exactly. Of course, we have to improve the robustness of our method as well. Currently, I would say that we have about 70% functional sensors. And so we can always pre-calibrate the sensors to ensure that we know what kind of response to expect in the clinical sample, but we just have to pre-test them. And so for the pre-testing, we need to upscale, and then to implement them for the actual clinical study will be a whole nother challenge in itself. But as you mentioned, it is more of an electronics problem, but of course, we want to improve our reproducibility of the sensors as well in parallel.
Thank you.
I maybe have one final question for myself before we have to wrap up. These channels are very small, only 10 nanometers. And you mentioned that because they're so small, they already block out many big molecules, so you don't have to worry about them anymore. But I would be maybe very worried about them for clocking the channels. Do you have any issues with that, for instance?
And so that's a great question. And if you have a bare capillary, it clogs immediately. But because we pre-clog the capillary with the DNA and we really tune the pore size so that we really fully clog with the DNA. And so it's a 10 nanometer pore, and we know that the DNA molecule is approximately 6 nanometers in size. We've characterized this, and therefore I think that we have a clogged pore that is transparent to ions and small molecules, but it doesn't allow large debris or large proteins to enter. And so what's been very exciting about doing in-brain measurements for the brain slices is that typically for patch clamp methods, you have to do a negative pressure in order to not have little bits of the brain get stuck. But in our case, we just directly put it into the brain slice with no issues of clogging. And up until now, we can do long-term measurements without too much biofouling.
Oh, thank you very much. Then I think we will conclude for today. And then only rest me to say that next Friday, we have our last 6 candidates, and then we will also hope to announce the winners. So thank you all for joining today's iCANX, and hopefully see you all next week again. Enjoy your weekends.
Thank you.
Well done.